Nora.
Hey.
Hey, good to see you.
Good to see you.
Yes. Hey.
Hey. Had fun last night.
Good.
Hello. I'm not the only woman here.
I certainly hope not.
Oh God, that's so embarrassing.
All right, it's my pleasure to welcome everyone to this event for in the honor of Andreas PODELSKI's 65th birthday. So we all here to celebrate his many accomplishments as a scientist, and I want to keep the introduction short. I think all of us will also share our experiences and with Andreas as we go along. So I'm very happy to introduce our first speaker, who's Thomas Ball. So Thomas is a partner researcher at Microsoft Research, very well known for his many works, in particular on the SLAM project, which was of course a hallmark in the sort of advancements of formal methods, in particular in industry. And so he'll share with us today some of the experiences of him working on that project, and in particular the involvement of Andreas in this project. Yeah.
Dankeschön. Guten Morgen, Damen und Herren. Ich heiße Thomas Ball, and now we get to English. Okay, so Andreas, welcome. It's time to get this party started. As you see, I came for a party. Abstract interpretation, software model checking, and beyond. It's been 25 years since the SLAM project started in 1999 with Sriram Rajamani and myself, and you joined us very early in those times to spread the good word from Patrick Rousseau about abstract interpretation. In fact, a lot of what I'm going to say really owes to you, channeling abstract interpretation. The other thing I want to say is we're both dog lovers, and I was so excited to see this picture on the workshop page. What's the name of your dog? Zartine. Zartine? Tartine. Which means kind of sandwich. Oh, Tartine. Okay, Tartine meets Loki. So Loki as in, Loki, not the Marvel Universe Loki, but like, Wagner Loki, Nibelung and all that. Okay, so we're gonna talk about Andreas. So of course we have to start by going to Google Scholar and seeing sort of. I really want to know about the meaning of life, but that's a talk for another day. 1993. That's when I got my PhD. You were already producing lots of papers. But if you notice something about the years here, it was the early 2000s. So it was the start of software model checking, which was building on hardware model checking, program analysis, theorem proving, all these things coming together. And we'll talk a little bit about that time. So the overview of my talk, we're going to talk about safety, the early 2000s and the rise of software model checking, abstract interpretation meets the SLAM project. We had our first paper with Andreas, which was way back in 2001. And then we're going to, of course, we can't go on without talking about liveness and termination of processes as well as programs. And it really was a remarkable time where Andreas and Andrei Rebelchenko really started to tackle theoretically the foundations of termination of programs. And then of course we'll have a postlude. Okay, so in the spirit of the day, which is AI, we can't avoid it now, we move on to safety. So what could be more safe than a Samoyed driving a Tesla on autopilot? We move on to safety. And if you don't know, we did this little thing called the SLAM model checker. And what was that? That was, as Wes Weimer talks about very briefly in English here, not formally, SLAM is a software model checker. It abstracts C programs to Boolean programs and model checks the Boolean programs. No errors in Boolean programs implies no errors in the original, an error in the Boolean program may be a real bug, or we may refine the abstraction. So at a high level, that's what's now known as counterexample guided abstraction refinement, or CGAR. And that's what Sriram and I and others were exploring in the beginning of the 2000s. And so that was a really interesting time. Now we did more than just create the project and write papers. There was something called static driver verifier. So this was the idea that at the top here, you had all sorts of rules about how to write a device driver, and a device driver plugs into Windows and gives you access to peripheral hardware, whether that's a printer or a network card or things like that. And we would codify those rules that were in English in precise safety automaton, which was called SLIC, and an environment model to model the operating system kernel. And this SLAM process that Wes just described in English would produce defects like error traces, or it would say, hey, I couldn't find any other errors. And of course, there's a third unspecified arrow there, which would be the thing looping forever. But we'd just turn it off after a few hours if it didn't say anything. Of course, what did it analyze? It analyzed the driver source code in C. And so this actually, since 2004, this tool has been available and actually mandated by the use of device driver writers. And there was a core team, including myself, Ella Bonamova, Byron Cook, who will be coming later, I understand, Vladimir Levin, Jakob Lichtenberg, Kamak Harvey, Bohus Androsek, Sriram, and Abdullah. And we were the core team that implemented static driver verifier on top of SLAM and delivered that. And for many years, I think device drivers have been sort of this benchmark against which many software model checkers are measured. Okay, so back to abstract interpretation. So in 2000, Sriram was coming from model checking, I was coming from program analysis, and Andreas came in 2000 with the declaration of abstract interpretation from Cusseau. You had spent, what, a year with him or so? Oh, just a month? Oh, okay, you're a very fast learner. So what I learned from, this is a slide that if you were at the Cusseau 30 years of abstract interpretation you saw, it was my synthesis of what I learned about abstract interpretation from Andreas. So the declaration of abstract interpretation was a statement of principles about program analysis that you should compare interpretations, different interpretations of abstract interpretations of a program, you can compare different interpretations to one another, you can compose them algebraically, and by all means you should celebrate infinity. Like if you do a finite abstraction, just go away. So these, and I also love alliteration, so CCC. So we had CC77, and in the spirit, 3 Cs. That's how I always remember abstract interpretation. We're always doing comparisons, we're composing new abstractions out of old ones, and by all means, we have infinite lattices. So at that time, I also said, well, where did the 3 Cs come from? So Galois, of course, was all about Galois connections, so that's the comparison. Galois there, and Turing, of course, the infinite tape and infinite programs. We have to celebrate infinity because, of course, these programs may never terminate. And then in terms of composing, then thinking of algebraic approaches, thinking of Scott, who was a PhD student, I believe, at Tarski. So this was, this was synthesized into Cusseau's mind. And of course, what happened was Andreas took that in 1 month. You knew a little bit about it before, right? Yeah, and he came to Redmond, and he showed us the way. Now, at that time, of course, I was steeped in data flow analysis. So data flow analysis, sort of from Kildall, is sort of represented by maybe the United States, and then abstract interpretation by France here. But they share sort of something in the intersection, which is, of course, a control flow graph of a program, semantics via semi-lattice and monotone functions and a least fixed point, but over on the top there, we're generally concerned with finite height domains, efficient algorithms, compiler optimization, right? Down here, compare, compose, celebrate infinity verification. So Andreas was coming from, I think, the lower right here, having visited Patrick and Radia, and we were very much up in the upper left here. So for those of you who don't know abstract interpretation, who has never heard of abstract interpretation or doesn't know what it is? Okay, we're going to fly through this. We have the integer sets in the upper left. That could be reality. That could be our concrete domain. We can abstract it various ways. We can do intervals, so we have a rectangular abstraction. We can go to an octagonal abstraction, which is more precise than intervals. And then we can go to like polyhedral, where we get a more precise abstraction, but there are many points still inside the abstraction that weren't in the original set. So that's the first idea of comparing. So what happened with Andreas was about composition. He came to Shriram and myself in 2000 and he said, well, you have this great algorithm that takes C programs to Boolean programs. Okay, what abstraction does it actually compute? And Shriram and I were like Homer Simpson, we were like, duh. I mean, we were just like, well, we don't know. We proved it correct. Like it's an over approximation of the semantics of the C program. And we proved it, it's sound. He's like, that's not good enough. You have to tell me precisely what the abstraction is. And so we were a bit at a loss. We didn't really know. So Andrea said, well, what you should do is apply the ideal. So we were doing predicate abstraction. So if we look up at the top, say we have 3 predicates, x greater than 5, x less than 5, and y equal to 5, and we're thinking about the effect of the assignment statement x gets y. By the way, I haven't talked about this slide for like 15 years, but it just comes back like yesterday, like I was riding a bicycle. So we can take the interpretation. We can take the abstract bit vector 0, 0, 0, and we can ask about its concretization into the actual state. Actually, I'm going the wrong way, right? That's concretization. So what does 0, 0 represent? It represents all the states S such that x is equal to 5 and y is not equal to 5, right? Because the predicates x greater than 5 and x less than 5 are false. So x must be equal to 5. Right? And the predicate y equal to 5 is also false. So 0 here represents the predicate being false, 1 representing true. Okay, and then what we do is we do a strongest post condition, and we would get this representation as a set of states that now x is equal to y and y is not equal to 5. And then if we abstract it back into the predicates, the 3 predicates that we would have, we would get 2 bit vectors. We would say, well, what you know if you're only in the world of the 3 predicates P is that either x is greater than 5 and y is not equal to 5, or x is less than 5. So is that clear? So that's the precise Boolean abstraction that you would get by taking a particular set of bit vectors, getting the formula, the concrete a realization of that, pushing it through the transformer. That's the best you can do with Boolean abstraction. Okay, but here's what we get when we apply SLAM. So we won't talk about the abstraction we compute, but we take 0, 0, 0, and SLAM, we get this. We get 4 bit vectors, which includes the 2 we got from the ideal. So something's going on here. We're not the most precise. So what are we then? And Andreas puzzled it out and figured it out. He said, well, what you've got is a case of Cartesian abstraction, forgetting. So Cartesian abstraction is you take a set of tuples and you approximate it by a tuple of sets, because there are too many tuples in your set, so why not just have a tuple of sets? And so if you take this precise description we got and you do the Cartesian abstraction, what you get is whenever there's disagreement in a position, you just essentially go to star. So really this, and then if we think of what the concretization of star star 0 is, it's the set that we had, that SLAM had. So basically what he's saying is like, yeah, you're basically losing information. You're losing information. You're losing the correlation between these 2 predicates that talk about y. Okay, and so SLAM abstraction was not, as perhaps Shriram and I thought, although I didn't even know we had the language to think about it, was not like the precise Boolean abstraction, which you would get by taking some bit vectors, abstract domain, concretizing, doing strongest post condition, then abstracting. Rather, it was this composition, right, where we did the Cartesian abstraction. Then we did the Boolean abstraction. So we would lose actually at the end there. Well, we'd lose on both sides. Okay, so that's what Andreas taught us, was that we really had to think about decomposing our abstraction into smaller abstractions, and only then could we understand what was going on there. Okay, so that's really, thank you, Andreas, so much. Andreas has always been about fundamentals and really understanding, digging in and understanding what is the key principles underlying, a process. And here, again, it was really his visit, and there are many other stories how Andreas explained SLAM to Cousseau, but I'll let you explain that. That's a whole nother story, right? And somehow you didn't quite convert him totally, but he came to understand it. He actually wrote a paper or something about finite abstraction, right? In the end. Yeah. Okay. So now we move on to termination. Okay. We can all go to sleep now. All right. So this is the slide that I had in Patrick's talk. At the time, Ratatouille was out. The thing about Ratatouille was the chef has infinite possibilities. Like, you think, oh, there's only finite ingredients, but you can make an infinite number of recipes. And in the same way, why restrict yourself to finite lattices? I mean, that's ridiculous. An infinite lattice, a chef with an infinite lattice, it's a recipe for tasty abstractions. And of course, Cousseau was all about this. Why restrict yourself to finite? And of course, this shows up in many domains. So when we think of really what is going on in SLAM, it's a process, it's not an algorithm, because it doesn't have a termination guarantee. So we take a program on the left-hand side, we take some predicates, we abstract it to this Boolean domain over here, we do some model checking of it, and if it passes, we're fine, but if we get an error trace, we have to do something to say, is that error trace feasible or not? And we can just go around this loop for a while. So the next question Andreas asked is, well, and many people ask, well, do you have any guarantee? Is it going to ever terminate? Because you can keep refining and inventing new predicates, and depending on the power of your logic, you may not be pleased. So here, Andreas came to the rescue again and helped us in terms of thinking about relative completeness, which is obviously a very well-known concept of this abstraction refinement for software model checking. So this is the abstract. Automated methods for undecidable class of verification problems cannot be complete. So Andreas said, well, let's think about an oracle that does widening. So during abstract interpretation, if things aren't terminating, you can jump and you can do this widening. And so there are many possible widenings. If you think of what SLAM was doing, or any model checker is sort of exploring a search space, well, why not incorporate widening into the search? You can choose different widenings at different times. And so the idea here was to compare software model checking to this fixed point iteration with oracle guided widening. And the result here was, I don't remember all the details, but it was basically, if there exists a iteration with oracle-guided widening that succeeds in. The other thing that was a big hit and spawned, I think, a whole nother research area was this search for ranking functions. So now we're talking about termination of programs, and you and Andre had this. Well, you first had this result that was at MPI. I was taught never to put citations in an abstract. So PR03, does anybody know what that is? Well, you had software model checking with predicate abstraction and termination, in MPI. You were at MPI at that time, and you had this cool idea of transition invariance. But here in this paper, which was the number one cited one, you had this amazing method for proving termination of unnested program loops by synthesizing linear ranking functions. And it was a really cool paper. I definitely recommend people looking at that. And you can basically solve a system of linear inequalities you derive from the program. And if you can get a solution, you can actually synthesize the ranking function. So again, it's a relatively complete method, again, if there exists a linear ranking function, this method will find it. If it's not linear, good luck to you. Right. So here's a little example with a loop where I think I is strictly, what is I strictly? I is strictly non-increasing, and j is strictly increasing, I believe, in that one. And you get these inequalities, and actually in this loop you can just look. The ranking function is it's just obvious, right? The ranking function is I minus j if I minus j is greater than or equal to 1. But your method would take any program, right, of a particular form and then derive this. So really, really nice. And this started a whole area of work with termination. You and Byron and Andre put it into a tool that was also run on device drivers. A lot of great stuff came from that. Okay, how am I doing on time, by the way? Okay, wonderful. Okay, so now we're ready to move to the postlude. Here we are, Andreas, you and I. You're sitting by the fire, your feet are in a blanket. I'm trying to play the drums, but I never learned how to play the drums. Look at me, it's pathetic. Okay, so what's happened since our days? Well, one of the things that obviously has powered the industry, and as a manager, I was really very lucky to hire great people. I hired Leonardo de Mora, who had already been working on Yikes and Sal, and he started Z3 with Nikolai Bjorna. And there were many people who we hired into Microsoft Research who then said, okay, Slam was great, but I can do better. So we had Synergy and Yogi, which was Aditya Nori. We had Solver for reachability modular theories. That was Shah's. Akash Lal and Shivendu Lahiri worked on angelic verification. So one of the things that happened with static driver verifier is there were about 4 or 5 different engines that over 20 years replaced SLAM, which was great to see. I mean, it was sort of like, oh, you know, there goes the baby, but that's progress, right? So really, you know, we were at the start of really something magical, and it was great as a manager to see, you know, all this happening. At the same time, you know, all good things must come to an end. So here's static driver verifier. I think this is maybe the first public announcement. 2024, Jakob Lichtenberg, who we hired in 2003, he told me, Tom, I have some news. Static driver verifier is being deprecated. So it's a 20-year run for a tool. So rest in peace, static driver verifier. But there are lots of good things that are still going on from all those days. We not only have software model checking, we have automated test generation, safety checkers, interactive functional verification. These are slides I used for years and years. Z3 and other automated theorem provers like it are powering automated test generation. These are tools still in use at Microsoft today for binary fuzzing, parameterized unit tests. Daphne, I hear, is getting a lot of use over at Amazon. Rustin Leno started that well over 10 years ago at Microsoft Research. F-star, you might have heard about as well, is also still going gangbusters. So although static driver verifier is being retired, there's a lot of other tools that have come out of the software model checking milieu that are with us and still getting a lot of use. And then of course back to software model checking. The Corral is the latest engine that was in static driver verifier and SimDiff, and those are still, I believe, active projects. At the same time, we've had many other software model checkers, and Dirk and Andreas had this wonderful review. If you haven't seen it, 20 years and beyond software model checking. So there we are, back in 1999. Probably Java Pathfinder. What was the reference there? I don't know what it was. But it predates SLAM. I'm sure there was something before SLAM, yes. And this is the growth of software model checking in terms of citations, right? Search results. And from their paper also, SVComp. So if you know, SAT solvers and SMT solvers all have their competitions, but as software model checking has gotten more prevalent, there have been benchmarks here. And I believe Corral has been used in one of those competitions as some other model, base of some other model checker. So thank you very much for this review. And it's really been amazing to go back and see all the progress. In fact, let's bring it back in the close to device drivers. So the prompt for this was a robot on a sled being pulled by Samoyeds over a snowy bridge. And the AI came up with that. So even though static driver verifier has been put to bed, we still think about device drivers, automata, and inference. So in closing, what have I been doing for the last 8 years? You can come to the talk. I've been thinking about embedded programming and this thing called the microbit. So it's all about device drivers. So we're teaching kids how to write device drivers, Andres. We're not using model checking anymore. But just a little bit about what I've been doing. There's something called the BBC microbit. It's been out there since 2015 with 8 million in over 60 countries with a web app called Make Code that's teaching kids how to program these things via a web browser. And then we have a little plug-and-play system so that they can extend this. So think of this as your motherboard. This is your computer, and these are the devices you're going to plug in. And so it's all device drivers, all again. And so there's a shameless plug for my talk at the end of PLDI. Please come to it, JACDAC, service-based prototyping. So I left formal methods for a while, but I've always been thinking about device drivers. Meanwhile, as I was reading your DVLP, I saw this paper, Craig versus Newton. So if anybody knows about abstraction refinement, Craig interpolation was like a big deal. But we had this algorithm that I came up with called for analyzing the trace of a program, and we named it Newton because Newton discovered things. It's stupid, right? But we were young. And we wrote a tech report about this, and I think we submitted it somewhere and it got rejected. But at that time, we were so busy trying to deliver the tool, we were just like, forget about it. So we had this pearl of an algorithm. I think it was interesting, and we didn't even get it published. We were so busy. But you guys formalized it, and then you compared it. So that was awesome. I didn't even know about this until this talk. So wow, our comparison of the Newton algorithm variance against Craig interpolation shows that Craig interpolation is clearly outperformed. Oh, this poor person who was just like, let me do something. I was just like, what? And then, of course, you spoiled it at the end. The conclusion one may be tempted to draw from the outcome of the experimental evaluation, maybe that Newton wins over Craig. Okay, blah, 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 blah. But but actually, thank you so much. That was a real gift. I hadn't been working in this area, and I'd always thought, oh yeah, there was that algorithm we never actually published. SLAM had so many ideas in it. We tried to publish it in the beginning with all the ideas packed in, and everybody was like, go away. So we broke it up into pieces, but we never got that piece published. So I have a gift for you. I've been working with Margus Vianis. I think you know who he is. And I think we're onto something big. I mean, you talk to Margus and you get sort of infected by his enthusiasm. We still haven't gotten it published, but we have symbolic automata, omega regularity, modulo theory. So actually I'm back. And I recommend looking at this. But in particular, if you want to know more behind the thinking, it's really Margus. The guy's a genius. And he has a little paper about symbolic derivatives and transition regexes. And the way I will say it is like, we love automata, right? But you lose something when you go down to control flow graphs. As we know, if you're out at the program level with formulas, you have algebraic reasoning. When you come down here, complement and all this stuff, it's like determinization, blah, blah, blah. It's interesting to say, what can you do up top before you go down? And so Margus has some really cool ideas. And derivatives are a very old idea, but there's a huge amount of power left on the table there. So Andreas, what's next? Learning specifications. For me, what am I working on? I'm actually doing this now. I was talking with Ahmed about it. Learning specifications of APIs from observable behavior. It's a very old topic. We're looking at automata, abstraction, model checking, inference. You should come visit us. Comparing and contrasting different approaches, and in developing some benchmarks. So I wanted to end with a chorus of thank you. Thank you, Andres. This is our latest dog, Eowyn, and we actually have another. I know this is going to get rather religious. We have a new baby coming. His name is Moose, and we all very much appreciate all your dedication to software model checking, to automata, to computer science, to theory, and if you don't mind, I will actually let somebody sing to you now. She's a dog who has been away from her owners for 3 weeks, and I just got this 2 days ago. Let's see what's going to happen. Oh no, we can't hear her. Oh, it's horrible. Well, there she is. She's very lonely, and she was singing. You'll have to believe me. Let me see. Oh no, we don't have. It doesn't appear we have. The demo gods are not with me. Let me try one more time. We're going to try one more time. But anyway, that's Eowyn singing for you. And so we thank. Oh no, I can do the singing. Yeah, I can do the singing. I can tell you what I auditioned. We probably have to move on, right? So Andres, thank you so much. I will let you listen to Eowyn howling for her owners. We've been away for 3 weeks. Yeah.
We do have time for a question.
Oh wow, goodness. Yes, please.
Just a remark. So I gave this talk on the completeness of abstraction refinement in front of Patrick Couzeau. It was a great talk, I thought, and everybody was enthusiastic. And then Patrick Couzeau, I know the difference between software model checking and abstract interpretation. Software model checking doesn't terminate. So that was his comment, to just. And he was bitter about the talk. He said people came to him and said, "Oh, now widening is obsolete," and so on. So
Oh. All right. Well, there is Eowyn, and she is happy for you, but sad for her owners. There she is. Oh, so sad. Oh look, yeah, I don't know why the sound's not coming out. I think there must be some setting on the computer. Okay, we'll let it go. Any other questions? There she is, singing for you.
Did Boolean abstraction make it to SLAM at some point?
Oh, you mean, yes. In fact, I remember sitting with Byron, so we had we had an algorithm that did fix-up. So it actually was by Satyaki Das, I think. I think that's the name. So there was basically, you could figure out in the trace where the Cartesian abstraction was biting you and add constraints. So yeah, we actually had a loop inside a loop. we had this loop where we would check. It was Satyaki Das, and I think Shivendu maybe pointed us to that algorithm. Then Byron and I implemented that. So yes, we did fix up, but we didn't compute precise Boolean abstraction up front. We still did the Cartesian abstraction, but then we did this fix up as needed. Yeah.
So since Thomas is too modest to say this, I mean, Thomas implemented also this refinement that then gets you Boolean abstraction in shape analysis. So this was probably 2010, right? And
Yeah,
what was what was the algorithm?
You mean
The title of the paper?
It was. I'm trying to remember.
Yeah. It's too long ago. Okay.
Okay, hold on, I have it.
I'm so sorry. What happened? What's the matter? I gave you a chewy. Is that what's the matter? You didn't like the chewy? You think I was going to abandon you?
She can sing with an object in her mouth.
I see. Oh, okay.
There we go. All right. Fine.
Let's thank Tom again.
Thank you.
So next speaker will be Dirk Beyer. So Dirk is very well known for his efforts in sort of making verification tool development not an afterthought, but really a part of the science. And he has put up tremendous efforts into SVComp, BenchXStack, and many other efforts, and will tell us something about all these efforts and how Andreas' group contributed to these developments. So let's welcome Dirk.
Thank you very much for your introduction. It's a pleasure to be here. And my name is Dirk Bayer from LMU Munich. And I would like to give a talk about find, use, and conserve tools for formal methods. And what does this have to do with Andreas? So first of all, congratulations, Andreas, not only to the birthday, but also to the many achievements in research. And since Tom has talked already about the theoretical results, I would focus on tools here. So you and your research group have developed a lot of tools, and they had a lot of impact. Two prestigious examples are the family of Ultimate, the family of tools for software verification, and as SMT Interpol, the SMT solver. Both have had enormous influence on the research community and have taught us how to do things. And by the way, Ultimate Automizer, for those who don't know, is the world champion of software verification, actually 2 times in a row even. And so these tools... It will be from now on always? Okay. We will try hard to change this. But it's hard to succeed with this goal. So there are excellent features and performance, and there are lots of medals also in the competitions. And the open problem is there could be a day when Andreas doesn't come to university anymore and enjoys wine and life and food and whatever, his wife and Elsa's. And then what happens to these brilliant tools? And this is what my talk is about. So my humble contribution to the work of Andreas will be to conserve tools, or to show a method how to conserve tools so that the tools survive the office or the times when Andreas is in office. So our vision that we have is, well, all the tools in formal methods should work together to solve hard verification problems and make our life safer and more secure, as Tom pointed out earlier. Model checkers and theorem provers should be integrated into software development process as seamless as unit testing today. Model checkers, theorem provers, SMT solvers, and testers should use common interfaces for interaction and composition. So this vision is hard to achieve. It could be a long-term challenge, but I want to show a few little steps towards this vision. So first of all, let's talk about the find component of it. So, which tools for software verification exist? I don't want to ask you for names, and you know one already, Ultimate Automizer. So let me ask a simpler question. What do you think, how many tools for software verification for the C language are available today? Who thinks 10? Who thinks up to 20? 23.
65. I go higher. I want 71.
Okay. How do you know, where do you get this number from? Is it a guess or did you look up?
I can't see it in what I go.
So actually the number of tools for verifying C programs that participated in the last competition were 59. 59, yeah. So, and counting also those that are meant for validation and can generate tests, we would have 91. So, so it's amazingly large number, and some of you were smiling when Ranjit said 65. So it's hard to know, right? So we need to do something about this. So this is one thing that we have to improve. So what can we do to support people finding our tools for test case generation or for SMT solving or for hardware verification and so on? And the next, once we have done this, that people are able to find our tools, we need to make sure they get reused. This is a next question. So out of these 59 or 65 tools, who would expect that you are able to get the tool running within 10 minutes? Okay. Who would say I am able to get the tool running within half an hour? Okay, so this is really embarrassing. And this shows us the state of the art, right? So we have the tools, we can maybe find them, but we cannot use them, right? So why do we have them? This is the next thing. So we have to do something to to make it possible to easily get the executables, to find documentation, to get them running. And then the next question is, even if you would have the tool and you would know how to run them, then you would probably have the wrong machine, not installed with the good operating system and with the packages you need. And this is basically the third big thing to conserve. So we have to specify what operating system does it need, what libraries does it need, what's the environment in which it can run. And this is what I would like to work on. And the requirements for a solution would be, okay, it must support documentation and reuse. It must be easy to query and generate a knowledge base out of it, because we want to find. It must be long-term available, and it must also ensure long-term availability of the tools, availability of the tools. It must come with tool support, and the approach must be compatible with the competitions, because the competitions are really important for our research area, because it keeps us, it keeps the tools up and running, it keeps them maintained, and it gives us yearly evaluations, comparative evaluations of the tools. So we must support competitions also. So the solution, the little step forward that I want to propose is a central repository that gives information about the tools, where to find the tool, and in particular, make it identifiable via a DOI, just like other literature, so software is literature in a sense. What license does it have? Who is the contact about it? What's the project webpage? Where can I find more information? What options do I need to use in order to get the tool started as the developers would recommend to me? What are the requirements? Like what's a Docker container or virtual machine to start it? What are the limits to start with, and so on? And this must be done in such a way that it is maintained by the yearly competitions that happen in the field. So this is the plan, and next I will show you how this looks like. So we are talking about little YAML files that contain some information and which can be then used to query the information and do everything else. So I want to show you for the as an example one of Andreas's tools, Ultimate Automizer. So and this is how the information looks. Why am I showing you these technical details? Well, just to show you that it is simple, right? I want to make a case of simplicity here. So first we say, what's the name of it? What input languages does it support? Where do I find more information? The project URL. Where do I find the code for it? what is the license? So what can I do with the tool? This is very important. Can I even download it? Can I even execute it? How can I extract information like command lines and interpret the outputs of the tool? What's the version of this file, right? And who is the maintainer of this whole entry? And this entry goes on with, for example, specifying contacts. So if I have questions about the tool, whom can I contact? So here's a list of maintainers, with, of course, with an ID, with name, institutions, country, and where to find more information about them. The versions. So how do I specify a version of a tool? So I say, for example, this version has the name as PLDI'24. This was the version that was submitted to a competition. The version of the tool has a DOI. So this is the identifier which I can use to download the exact version that was used in the competition. And this is the options that I need in addition to giving the specification and the program as input. And these are the required packages that the tool needs. And here is a container that I can use to get the tool running. And if I don't want to bother with installing packages, I can, well, I shortened this a little bit. There's a full container image that everybody can use. If one is interested in the participation in competitions of the tool, and this is also supporting the organization of the competitions. So, for example, here we say that, okay, Ultimate Automizer participated in the competition as PLDI'24 in the track verification with the tool version. You know, this is a reference to the particular version that was used, and this is the jury member who was responsible for taking care of getting this tool into the competition. And last, there is a section where you can declare what techniques it is using and supporting. Of course, the list for Ultimate Automizer is very long. It would fill the slide alone, but I had to abbreviate. And you can also give literature about the tool. For example, here, I think the most cited Ultimate Automizer paper is thermal checking for people who love automata. And there's also competition contributions where the new advancements of Ultimate Automizer is described. Okay, so this basically is such a file. And what can we do with this file? Actually, this repository should fulfill the so-called FAIR principles. What does FAIR mean? Well, the stuff must be findable, accessible, interoperable, and reusable. Well, how is it findable? Well, there's an overview on the internet. So all the information is available on the internet, and we can generate a knowledge base. I will maybe show you later if you have time. It's accessible because all the data are open. It's retrievable via the Git, or via the GitLab API, and the format is YAML, so it's very easy to query. It's interoperable because there's a schema for it, so everybody can look up what's the syntax of it. And for the archives, we use DOIs. So with the DOIs, there's more information about the entries in Crossref or in DataSite or whatever they are called. And the researchers are identified with ORCID, and the researchers can give as much information about themselves as they wish there. And it's reusable because all the data are CC BY, and also each tool comes with the license telling the people what we can do with the tool. And of course, also the format for the tool archive is standardized. Okay, so now what about the environment? I said one of the requirements is we need tool support. So the data alone is only half of the story. We need tool support for it. So now if we have all these computers and we want to make sure we can run on them. And there's a tool that is called FMVEC. The meaning of the name is probably only understandable for Germans who know VEC glasses to conserve fruits or vegetables. Also, you have these glasses, and they are called. There's a company called VEC in Germany. So this is formal methods VEC, and it is made to run the tools. For example, Andreas's tools forever, hopefully. So what do? Is you call fm, this is a command line, so you say fmvec and then run. It's similar to, who knows, Docker, right? Run is the command for it. But here it actually downloads and installs and runs the tool in the specified Docker container. So this fmvec looks up in the data that I showed before, what's the Docker container that this tool needs, and where to get the tool. So it looks up the DOI, gets the tool downloaded from Zenodo, and executes it, right? And here, basically, it says, okay, which tool and which version of the tool I need. And this is, well, this is more of the command line. So what do I... What do I do? Uh-huh. Ah, yeah. Interesting. Okay, so there's also the property to check, we want to check, for example, the unreached call specification, and there's a file given. So you don't need any knowledge about the command line interface, right? So when I ask you again to execute, you don't need to look up, what command lines do I need to use. And the tool runs in a container. So even if you don't have Linux, if you have only Windows, it runs. Yes, Tom?
So, but that unreached call, is that something that's common to all
So yes, so basically you can give here a file with an ending PRP, and this is a syntax that is defined in the competition on software verification. This is an attempt to specify, to have a common language to specify what we want to check. And there are several, like 5 or so specifications that are very common, like reachability of some function call, which is this. Like there's a call function specified that must not be called. There is memory safety, there is termination, and there are some other, like data races and so on. So these are referred to with names, and this is just a shortcut, basically. The standard way would be to give a file there, and the file contains the specification in a format that the tool understands, right? So this is also an achievement of the competition. So we have 60 tools that understand the same language for the specification. So you need to learn only one language and then it works. Whereas in the community of deductive software verification, you have to learn the different languages for writing down invariants and requires and ensures, right? There is no standard for that. Okay, so how does the tool work? So there is this fmvec also handles caching. It starts the container and it takes as input some user-defined specifications and the YAML file that I explained before, and it will, support commands like fmvec run, or if you want to give own command lines for the tool, you can also open the shell with the tool installed in the Docker image that the tool developers want you to use. And here is the 3 main modes that the tool has. So this is the main one: download and execute the tool in the container. No knowledge of the tool is needed. Here you run with manual mode, M for manual. So it also downloads and executes the tool in a container, but you can give more command lines that are native to the tool. And the shell would spin up a shell for getting interactive. You can also use a tool as a web service. I know that for Ultimate Automizer this is superfluous because Ultimate Automizer has already a web service that users can use, which is very important for people to try out without bothering to install, and it's also important for teaching. for, you know, if you're in a classroom and you want to show how things work, it's easy to have a web service for it. So Ultimate Automizer has an own one, and this is an one that is transparent for the tools, so it works with any of the tools that are supported in this repository. And it does not only have a website to run the tool, but it also supports on command line via web API using a REST interface. So the user here sends a request with the information about the tool and the verification task, and the Coveri team service, that's the name of it, prepares the environment, like downloads the image, downloads the tool, installs the tool in the image and runs it, right? Invoke and bundle the results and sends it back, and Coveri team takes care of downloading the tool and execute the tool, and the tool output and the generated files are given back to the user as the output. Right, so this basically gives a way to execute tools on a remote computer that is maintained by somebody else. There was also an effort by Microsoft, the Rise for Fun, right? And this was a very nice tool, and many people have used it, but it was discontinued. So we need something as a replacement, and we tried. Okay, so the conclusion. So FM Tools, this repository collects and stores the essential information to do a certain number of things, like run a tool as a web service, run a tool in a conserved environment, generate a knowledge base about the formal method tools, and organize competition participants. And now I would show you this generated website where tools can be found. But how to get rid of? I don't have. So as I explained before, there are a bunch of YAML files with information. They are easy to retrieve and to query information, but we can also make this more user-friendly and to support the findability aspect of it. So here is a list of two. Oh, I'm talking about something that you cannot see. Settings. No, apply, keep. No, you see the same as I do. So this is a web page generated from the information, and now you can see, you know, what tools are around. So these are the 91 tools of it. Unfortunately, Ultimate Automizer has a disadvantage if it is alphabetically sorted. So you go here, and here you see the information that you need to know, you know, if you want to see, is Ultimate Automizer something for me? So you look at, okay, what does it support? It supports algorithm selection, automata-based analysis. It's good if your program uses bit operations. It's using CIGAR. It's using predicate abstraction, ranking functions are supported, and so on. And what is it based on? So it's based on good. It's based on good stuff, high quality, you know, components, as you can see. So it's expected to run stably. here is literature if you want to read about it, and here is even presentations. If you want to learn something about it, you can get a quick overview of the tool. And yeah, if you want to look up the what it has competed in terms of competitions. Of course, this is still incomplete here. It has only the last year and not all the last 10 years. And yeah, this concludes. Thank you very much for your attention.
Any questions or comments, Dirk?
You said you want to preserve the tools, but still I see maintenance persons are still behind it. So if these persons sort of turn away from the tool, what happens then?
Yeah, so yes, so we have. So you are referring to this part of the information, and so these are the maintenance of the tool. If they become inactive, that's of course a problem because we don't get the good advancements of it. But here we know that the tool in this version is archived at this DOI, and this is a Zenodo DOI. Zenodo is government funded by the EU, so it's a CERN feature at the CERN project, and we hope that it does not disappear. So the tool will be what we call forever available on this in this digital library Zenodo. So we can download it from there, and the Docker containers, they will also be available. Here I use IDs that are currently available and make it convenient. And now you might argue Docker also at some point might discontinue, but we will also store these Docker images on Zenodo so that they are also retrievable in the future. Ranjit had a question?
Is this on? Okay. So my question is, if you go back to the beginning of your talk, your thing was how do you think you can run it in 10 minutes, 30 minutes? That was a question you asked, right?
Yes.
Now, one of the dimensions, sorry?
Install.
Correct. Install and then presumably run as well. Now, one of the dimensions that I think you have not considered is you're assuming that, so it means you're focused on C over here, right? But if you sort of generalize, but it applies to C as well, is C is not a static thing anymore. And so when you write these tools, you are targeting it towards, some version of C that exists right now. And 10 years later, we're in this regime where Andreas is enjoying, how did you say, wine and so on, right? And is not coming into the office. So C sort of evolves. And now if, newer C programs may simply not run on your tool. So what thoughts do you have on that? So all of this is, you're making it super easy so that the same set of benchmarks will continue to run regardless of where Andreas shows up, right? Because you've got this nice sort of Docker freezing and so on and so forth. But the language itself is changing where, people are going to be adding little pragmas and this and that and little syntactic constructs. And so the tool itself has to change. I mean, do you have any thoughts over there, or is that a kind of lost cause?
That is a very nice and interesting question, and I could talk about it for a very long time. So the short answer would be, I don't have a good answer. So this is an effort to conserve what we have. So we cannot predict the future. So we can only say, okay, what is available today, we can conserve and we can make it easy to use. And if the maintainers of a tool decide to support the most recent features, then this machinery also supports it. On the other hand, there are, it's not connected to this topic, but there is a research, a research group or research area starting about transformation, where you might have heard about this MOXIE intermediate language. And there are actually also existing intermediate languages for programs. So if we have a network of transformations that transform programs from one programming language into another, then we could also overcome the problem that if we have a new feature and we want to use an old tool, we could transform the program into a C program in the old style, in the old language, and then we could use the old tools. We have an interesting movement going on where we try to bridge the gap between hardware verification and software verification. So we are nowadays, we are able nowadays to use hardware model checkers like ABC and AVR to verify C programs by converting C programs to hardware circuit languages. And also the other way, we are using software verifiers to verify hardware circuits like in B2 or in IGA. And this makes it, well, this makes me hope that this is possible, that we can transform the new features to an old language, if we even can transform between software and hardware, right? And yeah, let me stop here with.
So I'm very interested in general, and goes back to SLAM, in sort of learning API specifications. So currently, I'm looking at it from a black box perspective in testing. But I wonder with these tools, I mean, they're learning invariants, they're learning something about the code, and at a certain level of abstraction, say the interface abstraction, you could persist them, but you could also compare them. You could say, how do different tools represent, you know, precondition, postcondition for a C function call, and then you could actually like take those formulas and maybe compare their strength in some logic relative to one another. So I'm curious to what extent, and this is related to deductive verification and the problem you previously stated about, you know, different languages. But I'm curious to what extent you've looked at, or the competition has looked at ways to surface, you know, intermediate, more knowledge. I mean, these automated engines are computing something, but it's not really being exposed, is it? And if so, why not? And do you have a path towards that?
I'm not sure if I completely understand. I think one of the answers is that the automated software verification tools, they are exporting witnesses, verification witnesses,
right,
and they contain invariants, for example.
Okay.
So about, like, you, a part of your question was, do they expose their results? Do they expose their what they found out about, right?
Right.
And current state of the art is just invariants, not requires ensures.
I see.
But the all these C verifiers that are supported here, they are exporting a verification witness that can be either a correctness witness, then it contains the invariants that are needed at loop heads to prove correctness.
I see.
Or, and basically, and then there are also works on taking these witnesses and transform them to annotations. Like you take a C
yes,
program and a witness, and then you compile that to an annotated C program. For example, in ACSL notation.
Okay.
Because you only need to peel out the invariant from the witness and put it in as annotation.
So you have examples where like somebody creates the witness and another tool consumes it?
Yes.
And checks
There
it? Oh, okay,
There are
great.
papers about this,
Oh.
yes.
I'm behind the times here. Yeah, thanks.
So let's thank Dirk again.
Thank you.
So we have a coffee break now, and we reconvene at 10:40.
you joining? Thomas talk.
Welcome back to the second session. Our first speaker is Thomas Wies. Thomas is a professor at New York University and the first official PhD student of Andreas in Freiburg, which, like, if you quantify us, like, you are the first in anything. So, Thomas.
Okay, thank you. Yeah, so being one of the PhD students of Andreas, of course, I owe a lot to Andreas. All his guidance and wisdoms over the years, and so I think he, of course, didn't just sort of tell us how to be a good scientists, but also I think what's important is that he sort of taught us how to have fun and celebrate while doing science. And so I think that's really one of the messages that he taught us. And if you look at it, I mean, clearly I needed some practice about the celebrating part back in these 20 years ago. Okay, so for today's talk, so this is sort of work we did recently, and I try to maybe motivate it a little bit by Andreas' work. I think everyone agrees that Andreas always sort of tried to distill into us that we should strive for simplicity, for elegance when we find solutions for problems, and really truly try to understand the problem. And that's certainly something we are striving for. And also one of the recurring themes, I think, is that he often sort of came back to automata theory as sort of one of the instruments sort of for really understanding problems and describing problems. And so in that spirit, I will be talking about session types today and our sort of work. We have an adapter here.
I have an adapter. Oh, yeah. Oh.
So next up is Jens Palsberg. Jens is a local, but also a professor at UCLA. Most notably known for his work on software engineering and programming languages. Those of us who worked on tools verifying Java obviously know him because he wrote the book on translating Java with Andrew Appel, which most of us use to build the static analysis tools. And after a little bit of setup, we'll get started on some.
Know the trick of how to.
I don't see your laptop, so I think that you have no.
Do you think that maybe the connection here is not real good? So that is funny because we are using.
Is the adapter? You try to find another.
Oh, this is the best port I have for sure. So. Huh?
It's the first Mac, right?
It's a Mac. It should work.
Try to share. I don't know if you are sharing your screen from the computer.
Do you know what to do?
No, because I'm not a Mac user.
Yeah.
I don't know, maybe because now you're not sharing. I don't see your.
I see. That's very funny. So this normally always works wherever I go. This is the first time it's like this. But maybe somebody else where it works. I can just share my slide with somebody else. They can use that computer. So,
I don't know if maybe it's the adapter also.
Sometimes try different.
oh, did you try the adapter before today?
No.
No. Then let me try my adapter.
Okay,
It's an HDMI?
Yeah.
I have an HDMI.
I think that what's up? Just the share.
I think this adapter is maybe not so good.
I don't know if it's.
I have an adapter too somewhere in my bag. Let's try this one. Okay, second try. Now at least something happened. So I think this adapter needs a repair. Oh, yeah, thank you. All right, good morning, Andreas. There's a great inspiration for this project I'm going to talk about. So 6 years ago, I started to work on quantum computing, and I want to understand the fundamentals, and what more inspiration can one get from this than following in your footsteps. I want to talk about optimal quantum programs, and really, we have a whole community now working on optimizers, compilers, tools for quantum computing. And the tools are getting better and better, and they will definitely help usher in the quantum revolution. The question is, my question is, how close are they actually to getting anything optimal, and what does optimal even mean? And so what I want to talk about today is really that I want to persuade you that really one can sometimes get optimal programs, and one can on a good day prove that they are optimal. And so I'm really diving into a fundamental question like we have seen Andreas do so many times. And so I'm going to go over 3 points. I will talk about some concepts of reliability that people use in quantum computing. Then I'll show you a couple of optimal programs, and then I will present a technique for proving that programs are optimal. And so that's where I'm headed. This is a quantum circuit. So I just want to sort of introduce the notation a little bit. This is we kind of got this from physics. They like to draw things that look like a circuit diagram. There are 3 qubits. They're called A, B, and C. Each qubit gets its own line. And then each of these thingies here is a gate. And so you can just think of it as a gate as we're used to in classical computing, except that it's gates in quantum computing. And you can see that sometimes a gate operates on 2 qubits, and sometimes it operates on a single qubit. And then the notation is sort of supposed to say what kind of gate we are talking about. And in quantum computing, it's applied linear algebra. So everything you see is linear algebra. So really, when you have 3 qubits, you have a vector of 2 to the 3 complex numbers. And when you have, say, a gate like this that works on a qubit, well, that's got to be a 2 by 2 matrix. And then a gate that works on 2 qubits, it's a 4 by 4 matrix. And that's really all it is. So it's just like all linear algebra all the way. And so time kind of goes from left to right as usual, and then the idea is that once you've executed all these things, you get a final state, and that's the result of your computation as usual. And as you can see, it's very finite. That's how it always is. So it's like, it's only the Popple people and the PLDI people who talk about infinite quantum programs. In physics, everything is finite. Maybe it has to do with that we know that quantum computing is sort of tends to be up against the idea of decoherence. And so at that point, it's like finiteness kicks in. That's where quantumness falls apart. But for what it's worth, quantum computers today are very unreliable. If we look at a gate like these single qubit gates, on a good day, on the best quantum computers we have today, reliability is maybe 99.99%, which sounds like a lot of nines, but it's, of course, if we compare with this laptop here, there's probably one error per year. So executing one operation with 99.99% is not that good. And these 2-qubit gates, it tends to be more like 10 times worse, 99.9%, just for executing a single operation. And so, so the first concept of reliability that people use is plainly to multiply up the reliabilities of these gates. And so you can see you don't have to multiply very many of these before reliability drops below 50% or 1% or something. And so that's why current quantum computers, they're neither big enough nor reliable enough to do anything useful. And I think we are like a decade or two away from that happening. But of course, we can still have fun studying the fundamentals until then. And also there's another thing. If our goal is to produce optimal programs, then working with an objective function that is the product of a bunch of reliabilities, that's a miserable objective function because it's highly nonlinear. And so people don't do that. So it's like, it's great to think about, this is really the sort of the ultimate objective function we should think about, but that's not what people study in practice for their tools. And so I'm going to go to another little bit friendlier notion of optimality, which is not the most reliable circuits, but instead the circuit that has the shortest, or the people would say the lowest depth. And so by depth, they simply mean how far is it from left to right, counting in number of gates. And of course, if the depth is small, that would tend to mean there are fewer gates, which means that the reliability product is smaller. So it's a good idea to try to decrease the depth. And overall, clearly, a shorter program should mean faster execution time. So this should be a very good idea to study this. And so if we think about how we would go about getting us a smaller program, I just want to give a quick idea of what is it we are doing when we are compiling quantum programs. And so really, I know that there are many good papers in PLDI and in Popple and so on higher levels of abstractions. But when it comes down to what the people in physics are studying, there are really only two abstractions. The first abstraction is that we don't have to use the gates that are supported by the quantum computer. We can use any kind of, really they're unitary matrices, any kind of unitary linear function we can use. And then what this translation step is supposed to do then is to compile to the gates that are supported by the quantum computer we want to run on. The second abstraction is that really when we look at the quantum computers today, many of them have restrictions on which gates, in particular 2-qubit gates, what they can do. And so if we just look one step back here, then you notice that I have gates here that operate like a 2-qubit gate operates on B and C, A and C. Over there's one A and B. Nobody says that the quantum computer supports all of that stuff. So that's the second abstraction, that we can just do whatever we want at the source level, but at the target level, we have to follow whatever is actually implemented there. Maybe there are only connections between A and B and C. So then we are back to the mapping step. That's what the mapping step is doing. So it's like insert some swaps is a typical thing that these compilers do that will then swap things around following what's implemented, and then we can do our work. So that's how it goes. So then we can say, okay, fine. So inserting swaps, that's inserting more gates into the circuit. That's going to increase the depth. And so it means that if we're going to try to do all this stuff, including solving the mapping problem, including inserting swaps, that's actually NP complete to get a minimal depth circuit. That's not so difficult to see. NP completeness, that means the compilers that we are using for quantum computers, actually, as many other compilers do, I guess, in classical computing, they are solving an NP complete problem somewhere along the way. And I want to say something about how hard a time people are having with that problem. So the reliability criteria, and I already said people are not even working on this. This one here, minimal depth, people are working on a lot. There are lots of tools, and it's not going too well. So I just want to go with a paper from my floor at UCLA, which I'm very fond of. So what they did was that they set up hard challenge problems. And then they say, okay, let's just run people's tools, people's compilers, and let's see how they do. And so what they do is a trick that was known from the CAD community from decades back. The way you challenge any tool that solves an NP-complete problem is that you make a really hard instance, and then you obfuscate it. And so in their case, what they do is they say, let's say we have this quantum computer over here. It supports 5 qubits, and these blue lines are the connections that sort of sets up which 2-qubit gates are actually supported. The other ones that don't have blue between them, you cannot just directly do what you would do at the high level. Now you have to swap around to make things happen. Then the second thing they do is they set up sort of like the core of the challenge problem over here. And that's just plainly a circuit. And there are these sort of free layers here just to sort of say, here's what we do at time 1, here's what we do at time 2, here's what we do at time 3. And that, it doesn't have to be an optimal program itself, but at least it's set up so it looks like very, very hard to do anything about that program. And then they obfuscate it. And so just to do a little bit more here, now they just sprinkle in gates just to make it hard to understand what's going on. And they're following all the rules of the quantum computer in front of them. This is like programming at the low level. And then what they do is they scramble everything. So this is the scrambling phase over here. They say, we were following the rules, but nobody says that we call our qubits exactly what they were called on the quantum computer. We'll just scramble it around. So of course, what is that? There's a whole bunch of different scramblings you can do, right? There's math that sorts this out. And so at that point, what you get is, in this case, there's the circuit. Give that circuit to whoever people's tool, a compiler we have in front of us, and let's see how well it does. So this paper here was published in 2020, so I think we should like redo all their experiments. But what they did at the time was that they picked some quantum computers that have something on the order between 16, 54, 20 qubits. And then they created these challenge problems. They followed exactly the recipe that I showed. And what they then discover is when they tried the Qiskit compiler from IBM, the Cirq compiler from Google, and what they discover is that the depth that come out is way higher than the optimal program. So of course they know how good it can get because that's where they started before scrambling. And what they find is that it's like 10x worse. So enormous numbers of swaps got inserted. And the state of the art has not gotten a lot better the last 4 years. People are still working on it, but another way of saying this is that if we really want to get to a sort of a mathematical understanding of what's going on, this criterion is too hard as well. So then we can say, okay, so maybe this thing with the depth is too hard. Maybe we should just go to number of gates. And in particular, as I said, the 2-qubit gates are 10 times on current quantum computers. They're 10 times more unreliable than the 1-qubit gates. So it would make sense to focus on minimizing the number of 2-qubit gates. And there are lots of optimizers out there. I sort of listed sort of my favorite ones here. There are more, and we can sort of just plug them in and just again take some circuits. It doesn't have to be these hard challenge circuits. It could be anything, and just see what happens when you optimize. And so I would say my experience is that sort of on a good day you can get maybe 30%, maybe a little less, maybe a little more. If it's a very hard circuit, maybe you'll get a lot less. But if you think of it as 30%, then I think that's pretty good. And so now it's like, okay, 2-qubit gates in particular, let's focus on those. Can we get optimal circuits this way? So I'm not going to discuss whether these tools give something optimal, but what I will do now is to simply jump to something that I know is optimal. And so that's my second point. So I'm going to focus on this fellow here. It's a famous gate. That's the Toffoli gate. It's a kind of a conditional gate. It's like an if-then-else with 2 conditions. So the A and B qubits, that's like the condition qubits. And then C is the target qubit. And what this thing is saying is if qubit A is 1 and qubit B is 1, then we do something to qubit C. And in this case, it applies an X gate, which is one of these gates again. And so it's like, okay, so most quantum computers don't support anything that operates on 3 qubits. So there has to be a translation phase that we map this to gates that's supported by the quantum computer. And what could that look like? And so I'll go through a couple of sort of translation steps, just with in mind that I'm going for the minimal number of 2-qubit gates. And so it turns out that if you draw this 3-qubit gates on 8x8 matrix, it's not diagonal. But of course, we know we can diagonalize stuff, and in this case, the diagonalization looks like this. This is a different 3-qubit gate sitting in the middle here, and it's a diagonal gate. And then all we need to do is to diagonalize by conjugating by something on each side, 1-qubit gates there. So no 2-qubit gates were introduced to do this. So our Toffoli gate is actually equal to this thing over here. This could all be written out in math, but I thought this is a birthday talk, so we'll just draw pictures. And indeed, this thing here can be written, the notation people like is sort of control C, and it's very much a diagonal matrix. So there it is. It's like, okay, so this means that now we can focus on seeing what's the smallest number of 2-qubit gates to implement this diagonal matrix here. This is like this is a topic that has been studied for a long time. I think the thing I'm going to show next, I think, was actually known to Feynman all the way back into the 80s, and people keep studying variations of this problem here. So this is the thing that I believe Feynman knew, which is, that's actually the circuit that I showed earlier. This thing here, if you start counting, is saying, see, here's it 1, 2, 3, 4, 5, 6 2-qubit gates, and then some 1-qubit gates as well. This is an implementation of CCZ, and in 2008, Shandy and Markov proved that this is actually optimal. If all you have is these CX gates, or C0 gates, as some people call them, as 2-qubit gates, then you cannot do better than 6. And so that's an optimal one. So you can see it took people quite a few years from the 80s to 2008 to prove that this is optimal, and this is absolutely not an easy proof. But instead of focusing on this one, I want to focus on another one. So here you're imagining a quantum computer that supports C0. So that would be like an IBM quantum computer. That's what they tend to do. But there are many other quantum computers, and they will support other 2-qubit gates in particular. And so to be able to talk about this in general, let's look at just using any 2-qubit gates. Doesn't even have to, just any unrestricted, whatever 2-qubit gates you like. And it turns out that now we can do it with 5. I don't even need 1-qubit gates here. You can see it's very clear. 1, 2, 3, 4, 5 2-qubit gates here. And so they do whatever they do. You can see they all have this structure of there's a control, there's a target. It's conditional gates, all of them. And in 2013, Yu, Duan, and Ying proved that this is optimal. This had been an open problem for, at least it appeared in the famous Nielsen and Twang book in 2000, whether this is optimal, and they eventually proved it. And as it happened, Ning-Kung Yu came out to visit me just before Popple in 2020. And so we talked about computer science, and he said, I somehow mentioned this paper. And so I have this thing that I'm teaching a sequence of 2 quantum courses at UCLA. It's like Quantum 1 and Quantum 2. It's like the survivors go to Quantum 2, but I've had something like 500 students come through Quantum 1 already. And I was in the middle of preparing for this Quantum 2. And I was thinking, oh, this is a wonderful paper. It's like 4.5 pages. And you know, a lot of it is text and references. The proof is 2 pages. So I thought, this is wonderful. It was a Sunday morning. I'm going to read this over Sunday, and then I'll teach this on Tuesday, right? Okay, 2 years and about more than 100 one-hour Zoom calls later with this Ning-Kung Yu, I finally understood the proof. And it's written up in LaTeX. In my version, it's 60 pages of proof. And I am going to say something about how this works. As an aside, I tend to give homeworks in my classes. And one of those homeworks is to see, well, maybe even if 5 is technically optimal, maybe you can get close. So I give a standard homework that is you only get 4 2-qubit gates. Just get as close as you can. And this is actually the best anyone has ever come up with. There are many, many variations of this, but they all come up with the same distance. There's a distance measure on matrices that I really like, called the Hilbert-Schmidt distance. And this one has the best Hilbert-Schmidt distance to TOEFL one can get, and it's not close. It's 0.38268, and if you want a formula with square roots of 2 in it, I can give you that as well, but it's not close. So nobody would use this as an approximation for TOEFL. It's too far away. And so, I just want to understand, why is this one then optimal? And I have really sort of done the Andreas thing of diving into the fundamentals of this, and I just want to give you a sense of how it works. So it turns out that there was a generalization of this thing, that we need 5 2-qubit gates to implement TOEFL. That was 2 years later by some of the same authors. And so this one here says, I'm going to sort of like read this out loud. It says something general that then implies what I said before. So the idea is that we want to show that you cannot get very far with the product of 4 matrices, a sort of a circuit of 4 2-qubit gates. And this is now formalized. So it says if we have a product of at most 4 2-qubit unitaries, that's equal to, now we are going to generalize to control anything here. It doesn't have to be X or Z or anything else, but anything at all. Then this happens if and only if that one qubit gate that's sitting here, either the eigenvalues of that thing are equal or the determinant is 1. And then you can immediately see that if we are doing control set, then if you just sort of look at the details of what that matrix is, that's a diagonal matrix of 1 and -1. Then clearly the eigenvalues of that are 1 and -1, so they are not equal. And the determinant's got to be 1 times -1, that's -1, so it's not 1. So it means that this theorem immediately implies that we cannot implement control set in 5 gates, in 5 2-qubit gates, and similarly for control X. Okay, so how are we going to prove this? That is my question here. So here's a diagram of my proof. So this just appeared in linear algebra and its applications. It's the first math paper I ever had, and have in a way, in the sense that it was published in a math journal. And so the proof goes as follows. I'm going to like hand wave my way through how to go about this. So in the actual paper, I have 50 theorems or lemmas that sort of spell this out. This is the highlight of that. The first point is we are starting with this general CCU. The first thing we do is we diagonalize, like I did before. So that gets us to theorem 7.4. Theorem 7.4 is the gigantic case analysis that takes all these different products one could think of for implementing just products of 4 things, products of 4 2-qubit unitaries, and breaks it down into, thank God, there are only 2 cases that captures everything. And those 2 cases are then 5.1 and 6.4. It's like there's a reduction that just reduces that to the general case. Now we can look at each of those 2. And so in a way, they are very similar in proof, except that this one is like 10 times more of it. So I'm just going to talk about this one over here. So what we do in lemma 5.1 is we say, okay, so we look at this particular case of a product of 4 unitaries. We don't really know what they are, but it's a case in the sense that the first one, say, works on A and B, and the second one works on B and C. It's like it's restricted in that way. And then we stare at it, and then we discover that it's almost like program analysis. If we take this product as a little program, we discover that actually, if that's equal to CCU, there's no way that these 4 matrices could be general. We sort of start to discover that they have properties, and in particular, we start to discover that they are conditionals, some of them. And then it's like, oh, so if we know they are conditionals, then we can go back and say, what did we learn? And then we can like do the product again, but now knowing that some of them are more special cases. And it turns out that that's where once we have discovered some things, we can plug in lemma 4.1, and lemma 4.1 then says, oh, but then, and then you get the result from the previous page for that case. In some sense, we could stop here, but there's still this question of where did this idea that the eigenvalues are equal or the determinant is 1, where did that condition come from? And it turns out that it comes from lemma 3.2 in this case here. So I'm just going to state lemma 3.2, and then you can get a sense of that this condition down here, it's still there. There are 2 things that are equal. That's like the eigenvalues, or the product of them is 1, so that's like because it's a diagonal matrix that it came from. It's like that the determinant is 1. And there's a much simpler property that we can now look at. So this gives me a chance to talk about tensor product. So in quantum computing, when you have two unitaries that work on two different qubits, the way we can sort of model this mathematically is to talk about tensor products. And so I guess today it's like there's no need to understand the details of this, but it is a way of combining two matrices, in this case 2 by 2 matrices, into a 4 by 4 matrix. And it turns out that if the eigenvalues of that is 1, 1, U0, U1, so that's something that comes up all the time, if it is the case that you can find such two unitaries here, then this is only going to happen if U0 and U1 satisfy these properties here. And so when you sort of dig down, way down under this property of can we implement TOEFL with how many 2-qubit gates, this is the lemma that we really, really need, and then everything just builds up on top of that. So we formalized almost all of this in Coq. The Coq proof is like 16,000 lines of Coq. What we did was that we started with Robert Rand's library, who had been working on formalizing quantum in Coq way before we started. And he has actually helped us along the way. There was a point in February where I had to to ask Robert for help. And so we had a bunch of trouble with the spectral theorem, but he solved it all. And we are down to one lemma, not even one of the 50 lemmas I mentioned, but a support lemma that's like obviously true if you ask a mathematician, but Coq just has trouble with that lemma. So we are working on that one lemma. So we're one lemma away from formalizing all of this in Coq. And then, as you can see, this is all linear algebra. It's just formalizing a lot of linear algebra in Coq. So it's very natural to start to talk to the mathematicians about this. So for example, the other day I had lunch with Lin from Berkeley, and it was just like talking about formalizing stuff in math. I also talked to Terence Tao at UCLA, who's one building away from me, and he said, "Oh, I like Lean much better than Coq." And it's like, what's your reason for liking Lean much better than Coq? He said, well, it's such a nice math community. We all help each other, and it's like we have this wonderful library that we build on. And so I have started to think about, does that mean that we should just move to Lean? So I feel really bad because I'm like heavily invested in the sort of POPL PLDI community, but I think the time may come. So I found 5 students at UCLA. Some of those know both Coq and Lean, thank God, and so we are going to start to work on it this fall. And so if there's any one of you who knows anything about how to go from Coq to Lean, experience, prejudices, biases, whatever you may have, I would like to know about it so that we don't ruin our fall completely here. But that's where we are going. So Andreas, congratulations. It's like that. This was a 2-year journey for me just to understand this proof. And this is like where we need inspiration from people like you to just stay with it and really try to say, I want to understand the foundations and the fundamentals. So happy birthday.
Thank you.
Will you ever run one of these programs on a computer yourself?
Yes, of course. Of course.
Have you?
Yes, of course.
Really?
But we run it, say, an IBM. So you mean the quantum part, not the Coq part?
Yeah. How do you get access?
There's online access. So sometimes it's online. Okay, so I have like a little story. So in the beginning, back in 2019-20, I ran into somebody who works at Rigetti, one of the quantum companies, and I said, could we get access for my class? And she says, yeah, we can probably work something out. So we sort of like maneuvered our way in, and we ran on Rigetti the first year. Then the second year, we are very well connected to Google. The guy who was the program manager for the Google Quantum project over in Venice, 4 miles from us, he's married to my closest colleague, Miriam Kim. And so we see him all the time. So it's like, hey, could we get to run on Sycamore, which was their biggest quantum computer at the time. And it's like, yeah, we can probably do something. So in contrast to IBM, which is famous for having this wonderful web interface, very automatic and so on, Google didn't have any. So we actually built the interface to run on Google's quantum computer. And then we got Colorado School of Mines in there. And then after we were done, they discontinued the whole thing and said, well, that was the experience with academics. We're not doing this again. So I don't know whether we ruined it for everybody. Now, after that, they only support researchers. So they don't want to give their quantum computers for teaching anymore. They only, if for research, I could probably get access to Google. Then we also ran on IBM, and I sort of forgot the rest. Now some
Well,
years
most of
have
the
passed.
students in your class must be just running on simulators. Or
They run on simulators for part of the time, but some of the homework insist on that they run on quantum
Oh,
computers.
okay.
Right? So it's like if you're going to convey excitement in this,
Oh.
you got to have at least one homework that runs on a quantum computer. Then you will see that it works like crap, right? That's a technical term. And then you go back to simulators immediately,
Yes.
right? But you got to get the experience just to get it into your classroom.
Thanks, Jens. And for the optimality part, and also for the foundational aspects of actually taking a problem and studying fundamentally. So in classic computing, we've studied actually, complexity and figuring out how much space and time, things are. So the basic model we've used is actually saying, like, getting access to something that's arbitrarily far away. That's 0, right? That's the random access model. But adding to numbers, boy, that we really count. So in practice, it means that all the kinds of optimizations we make have completely irrelevant. It's all about distance, right? So it's all about, and it's the same thing with quantum computing. So I'm asking, because it's even worse, you could say, because it depends on actually what technology you're using. So I'm asking the following thing: is like, are we on the way now, entering this intense, competitive, fun phase of studying something, optimizing it? That's clear. That's in the end irrelevant, because we're actually ignoring actually the complementary and much more important problem of actually layout, low dimensional layout of data and all these things.
So I have an answer, but it's not a layout answer. So Ryan Babush, who runs the quantum algorithms group at Google, came out to visit us a month ago, and he gave sort of all the last papers of the last 2 years, I think, that they had produced of algorithms, and he tends to count either T-gates, like I had an example, or TOEFL gates, actually, that I talked about a lot. And so I asked him, why are you counting those things? And he said, because we are looking ahead to that there will be a day when we have error correction on the quantum computers. And at that point, the things that will be really expensive, sort of really, really expensive compared to everything else to execute, will be T-gates, or more or less equivalently TOEFL gates. We can have a discussion about that. And so he said, that's what you should count. And so the last month, I've actually more or less made it a point out of every time I meet somebody in quantum, I say, by the way, do you agree with this? And so far I've gotten yes, 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 100% yes. So I think that the point here is completely correct, that we should know what to count. And I think the day will actually, what Ryan said to me was, I said, I'm counting 2-qubit gates. And he said, oh, this is such a NISQ thing. So NISQ stands for the near-term intermediate scale quantum computing. So it means it's more or less the 2020s, not very large quantum computers. It's not really working that well. And so we are counting 2-qubit gates because they're the most unreliable. But once error correction works, then that point ceases to be as important as what's really hard to implement, and that'll be T-gates. So
but it's still the gates.
it is still the gates and not the distance. So I think that so this opens up a whole other thing. So now there's a whole different topic that comes in, which is like super unresolved, which is what is actually the future of error correction. And it looks like quantum error correction is due for a revolution the next, I would say, 24 months. I talked to lots of people in the community, and there's this new thing called LDPC codes, low density parity check codes, that is going to revolutionize everything. And they will just dramatically change how many qubits we think we need to support one like source level qubit. So right now the conventional wisdom is 1,000 physical qubits to support a single logical source level qubit. That number is going to drop. And once that number starts to drop, we'll start to get much more realistic about, okay, so what are the resource requirements here, and what should we be counting for thinking about optimality? And then I think your point comes back in, that the actual layout of the qubits is going to be key again. Right now there's this gap between that the error correction people are over there and these sort of mapping people are over there, and they don't talk a whole lot.
I think we have time for one more. If not, let's thank Jens again. And we'll back here after lunch. I'm being told that the lunch is downstairs, but I haven't seen it.
Right, welcome to the third session of these festivities. I'm introducing Rupak Majumdar. He's like Andreas, he's coming out of MPI, Max Planck Institute. He's still there as a scientific director. He's like Andreas in the neat parts of Germany, I would say. Like he's in Kaiserslautern, kind of close. Also, I've seen him at many PhD defenses, and so he helped bring people up like me, not my defense, but still. And I also have a colleague at Satora who worked with him, Jaroslav Bendik, and his interests are in verification of X, for X being very many things, and in automata theory.
Thank you. Well, thank you. It's a pleasure to come and talk here. And of course, Andreas and I have known each other for a very long time. I was an intern in Saarbrücken MPI at the end of my first year of PhD, and Andreas was, of course, there. And I think one of the discussions during that visit was a discussion with Tom Hensinger, how model checking and verification can never really work for software, right? I think you probably remember this. And then I was interning with Tom Ball and Sriram at Microsoft, and Andreas came for a visit that Tom talked about. But then, about a year later, I was at LIX in Boston, and I was kind of a beginning graduate student, and I think what was extremely special for me was that Andreas and actually Shankar came and had a discussion with me as equals. We were all discussing what's the next thing for the important problems of the thing. And that was really a very nice turning point for me as a young graduate student to be taken seriously by famous people. And since then, of course, Andreas and I have had many discussions about many different things. And the talk that I'm going to give today is about some work that I've been doing over the last couple of years at Amazon with a bunch of people that's working on roughly software verification. And I want to start by saying that, well, there's all this work going on in sequential verification of software, including the things like SLAM and so on that we talked about. And the natural question is, what's going on with the verification of distributed systems? And to be honest, distributed systems are really where the money in software is being made, right? So if you think about Amazon, well, it's a very big distributed system with many, many different services. And the question is, these systems are complex, they fail in very unpredictable way. What tool support can we give to people who are working in this area, right? So who are building these systems. And in this context, I remember that there was a very early meeting about software verification at SRI. I think, Shankar, you organized this Grand Challenge workshop. And there, Amir Pnueli had this thing that, well, as far as model checking was concerned, well, hardware was a distraction. Software was where we wanted to get to. And I think what I would like to tell you here is that sequential software was a distraction. We should really get to distributed software. Okay. Now that we have solved all problems there. Yes. Okay. So now to the more technical part, well, I'll talk about the MUST project, which is something that we have been working on at AWS with many people who are also in this room and others. And the goal of this project is essentially to see what it takes to look at distributed system implementations and be able to reason formally about these implementations, right? So what are the kind of systems? Well, at the core of many of those services that I showed you are some very core distributed algorithms. For example, there is something called a distributed replicated log, where essentially you have a number of clients who can send write or read requests, and you want to make sure that each reader of this log essentially reads what has been written in exactly the same order. Okay, so if it's a sequential object, then this is very easy to do. It's kind of a shared register, if you wish, or a shared vector or a queue, right? So whenever a write request comes in, you insert it on the queue. The read request kind of reads the queue left to right. But the trouble is that if you have a distributed system where these clients are coming in and you have to somehow make sure that this whole thing is fault tolerant, this becomes a rather complicated piece of software. And you have to make sure that, you know, even when some of these internal nodes of this replicated log goes away, the clients still have a consistent view of this service. Okay. Of course, if you can build a primitive like this, then you can, for the most part, ignore many of the core distributed systems and build a lot of things on top. Okay. And this is indeed so, right? So, you know, you have some core primitives like Paxos, you have replicated logs and so on. And this allows many of these very large-scale systems to scale without everybody having to talk about every possible asynchrony in the network and every possible fault in the server. So you can think of these as abstractions that are very important. And the goal is, how can we reason about these core systems that provide these abstractions? Okay? And just as an example, here's how a replicated log protocol might work. You may put a bunch of servers kind of in a chain. You have some coordinator that for the moment we can ignore. It's there for fault recovery. And when a client comes and writes a request, you kind of write each node in this network writes to its own log and then forwards a message. And so it kind of goes to the tail. And once it gets written on the tail, then it sends an ACK to the client saying that, yes, this write has been done. And then when a client comes and does a read request, it goes directly to the tail and tells you the value that's written, right? And with a bit of thought, you can figure out that this is a very consistent view of a replicated log. And the harder part is that, well, you have to make sure that this replicated log works as advertised, even when certain nodes fail. And this, again, is something that you can do by the coordinator by setting up new links and making sure that this additional data is forwarded and so on. Okay. So these are the kinds of systems that we would like to verify. Okay. And of course, you know, you can get the algorithmic description that if you have a protocol like this and with k nodes in this chain, then it can tolerate k-1 faults. But of course, when you look at the implementation, there are many, many other issues that makes writing these systems very difficult, right? So the algorithm or chain replication probably fits into half a slide. The implementation that you would actually deploy is probably many thousands of lines of code. And those thousands of lines of code are there for good reason. Okay, so how do you gain confidence in your implementation? And this is where this MUST project comes in, and it's part of a much bigger picture of, you know, how do we reason about concurrency and distributed systems. But I will just focus on a tiny piece of it that we have been building. And this is essentially allowing model checking to work directly at the implementation level of these distributed systems. Okay. So MUST essentially consists of, well, you know, there is a modeling library. And you can think of this modeling library as an embedded domain-specific language sitting inside Rust. Well, why Rust? Because, well, there's a lot of interest in writing many of these core protocols that have to be very performant in Rust using the type system. And, well, in general, what MUST allows us to do is to take some of these nice things about the Rust type system to be able to do some checks that would have been quite difficult to do otherwise. So it's a modeling library for message passing that's embedded in Rust. It gives a generic partial order semantics of these message passing programs. I'll get to that in a second. And then it builds a lot of abstractions on top of a very core language. Right? So to the programmer, there is not really much difference. You know, they're using TCP listeners, they're using RPC calls and so on. But internally, the semantics of MUST makes sure that all of these things are understood in terms of the sends and the receives that MUST provides. The second part is a model checker. I will talk a little bit about the algorithms that go inside this model checker. And the third part is more, you know, somewhat of a higher level discussion of many of the things that I learned in trying to take an academic idea and trying to see how it turns out in the real world. Right? Okay, let's just focus on the first part. As I said, so a must model is essentially a normal Rust program using certain special API calls. And what are these API calls? Well, if you're trying to model a distributed system, you have to have some way of modeling the processes. You have to have some way of saying what these messages are. You have to specify the communication. And as many of you know, if you want to have a language that is somewhat that can abstract away from all the details of an implementation, you have to have some way of giving non-determinism, right? And so the very core must library is really very small. It gives you a way to spawn a process. It gives you a way of sending messages and receiving messages. So you know, as a process, you can send a message to another one. As a process, you can wait and receive a message from another one. And then you can have a non-deterministic choice baked into the modeling language. And then you have some kind of an assume that says, well, execute up to a certain point, check that a certain condition holds. If this condition does not hold, pretend that this execution never even happened. Okay? And roughly, these are the 4 core primitives, right? So this is the core language on which you build your semantics. Everything else is abstractions built on top. And the semantics that we give is directly as partial orders that you can get out of this execution. We call these execution graphs because this notion kind of came out of the weak memory semantics, and then more recently in the sort of looking at shared memory DPOR algorithms. And the idea is that you have some kind of sequential computation that's going on in each process that you've spawned. And then there are causal links between the send events and the receive events. Okay? And the particular set of causal links that you're allowed to have is given by something called a consistency model. And the consistency model just tells you when you have a receive, what are the messages in this graph that can actually flow into it. Okay? And you see that this consistency model may be different for every kind of model that you have. For example, a TCP send may have a different semantics than a completely asynchronous send, right? So if there is a TCP send, then if there are 2 sends here, then this one must be received before the next one. But if it's a completely asynchronous network, this ordering may be changed. Okay? So I lied a little bit by saying there's only one send and only one receive. Essentially, for each of these kind of core semantic notions, you would have to have some, a corresponding notion of a send and a corresponding notion of a receive. And then the consistency model will tell you what causal links you can have in this graph. Okay, so this is roughly the core modeling language of must. And this is surprisingly versatile. You can do a lot of things with this. And the must model checker itself is a stateless exploration engine, which does very aggressive partial order reduction. Okay? And this partial order reduction is computed directly on these execution graphs. And what is quite important is that the model checker kind of knows many of the abstractions that we do on top of this very basic set of primitives. And by teaching the model checker these abstraction tricks, we can actually scale much better than if the model checker had no idea what is going on, right? So we can talk offline about specific examples. So the DPOR algorithm, again, is it's kind of a variant of a classic DPOR, dynamic partial order reduction algorithm. It kind of executes the program, and as it executes the program, it constructs this graph on the side. And then once it has finished one execution, it looks at these causal links and figures out which ones you can flip to give another consistent execution. And it keeps doing this until there are no more executions. Right? So I will just skip the particular details, except for to say that, well, the algorithm that we have guarantees 3 properties. First is completeness. So if you have a program, then this musts algorithm is guaranteed to exhaustively look at every non-isomorphic execution graph. And it's optimal in the sense that each of these graphs is looked at exactly once. And the point is that you do this with only polynomial memory overhead over the memory overhead of the program. Right? So getting all of these three things together is slightly complicated, but this is where the core idea of the model checker lives. Okay. So for example, this kind of partial order reduction is extremely important, even if, when you look at these kinds of protocols. For example, in this chain replication protocol, if you don't have any faults, then the number of executions that you need to look at is independent of the length of the chain, right? So if you have a number of concurrent write requests, then the number of executions that DPOR will look at is essentially k factorial, which corresponds to the order in which the clients put the writes into the log. But the length of the chain is actually irrelevant. Okay? And this is certainly not so if you did not have partial order reduction. Okay? So for example, if you just had 2 writes, well, these are the 2 message sequence charts that you get. And already you see that there are 212 sort of traces of executions that you can get. And in general, there's a very large number of executions. I will skip over how we deal with the sort of lower, how we build abstractions on top of these specific core primitives, and go directly to say that, well, we have applied the model checker to a number of things that you would expect. I don't want to bore you with the numbers, but the point is that this very aggressive partial order reduction allows us to finish exhaustively exploring systems for which, without doing any of these reductions, we cannot finish. Right? So there is certain things to be said about being able to exhaustively explore even a small number of requests on a complicated implementation of a distributed system. Aggressive, well, okay, this is, I don't know. Let me say that it's optimal, right? So, yeah. And it's aggressive in the sense that, we give the semantics directly in terms of the execution graphs, right? So we are never even, thinking in terms of these traces. And just by thinking about these execution graphs as the representations, you can get this kind of an, optimal DPOR with small memory overhead, right? So. Okay. I will talk just a little bit about, going from this first part, which is all very nice and scientific and clean, to what happens if you try to make it into a product, right? So the first thing that I realized is that, whatever new and complicated verification technique that you introduce, it has to really fit into the way the developers are doing their work, right? So if the developers have to change their work in very complicated ways, there's an additional inertia, right? So I think a lot of the work that went into taking this core algorithm that was written in a few months into making it into something that an engineer who has no exposure to formal methods can actually use. It's actually a very large amount of work, right? And along the way, you kind of realize that, well, just because there are many publications, it does not mean that, well, some problem is solved. You cannot hope to say that, well, we have this super cool technical idea, now change whatever you are doing and use this. And just the fact that, well, you think that you have a better technology, that it makes into a better product. Because I think that thinking about product is a very different skill set than thinking just about the core ideas that get into the product, right? And at this point, one of the things that I initially struggled with is this Byron's idea that, well, everything has to be sound, right? And initially it's very constraining, right? Because if you're doing testing, as long as something runs, you are kind of happy, right? Because, well, look, my tool ran. Right? On the other hand, it's a bit embarrassing because, what you're doing in a pure testing tool is that, well, at the end of the day, you can say, I did a local random walk in the space of, space of random choices in a program. And the obvious answer is, so what? So you did this random walk. What can you say about the system, which probably has billions of behaviors and you've picked, I don't know, 100 samples, right? So in some sense, thinking about this very constrained situation where your goal is to make sure it works on every possible behavior makes you think about optimizations that at the end may get you a better testing tool, right? So in some sense, just thinking about, well, I have this distributed system, but I have an equivalence relation and behaviors. And these equivalence classes are the interesting things that we need to explore. Not every possible trace is already something that can get you into a better testing product if you wish, right? It is quite possible that, you know, what we have done here is always going to be used in testing mode by the developers who are, who are actually using it. On the other hand, just because we thought through all of these kind of corner cases to make it sound, it kind of gets you into a somewhat better product at the end, because at the end, the natural question is, well, you have invested in, these testing tools and so on. What is your return on investment? And I think they're saying that, well, at least you get this kind of exhaustive approach at some level is a better sell than saying, well, I did some random exploration. But I don't know if you're going to, anyway. But of course, the other thing that you realize, and this kind of wraps up this talk, is that it's ultimately about the people, right? So when you develop technology, in some sense, you also are working with the people who are going to be using the technology. And this is always, this kind of back and forth is probably a very rewarding way of understanding what ideas to pursue next. And this is true not just in kind of making, a tool into a product, but also in research by itself. After all, the kind of things that we work on in science are largely determined by the people we like and our communities that we have around us, and the discussions and the fun discussions that we have doing them. So coming back to Andreas, I think he and I have this one paper with Jochen that we had a lot of fun writing. And I think that we spent an enormous amount of time discussing how to call this paper, because we submitted it to POPL. And we thought that the paper was very elegant and clean. And I think this was taken against us because the reviewers very dismissively said, this is not really a POPL paper, you can call it a pearl. Now, for those of you who don't know, pearls were supposed to be this elegant pieces of scientific work that should show up in places like POPL. But in practice, pearls had a somewhat derogatory connotation to them. It was like the piece of dust that's getting in our sides, and let's just layer it over, right? And then I think Andreas had a lot of difficulty calling his own work a pearl. And eventually, I think we wrote to Andy Gordon, who was the chair, saying that, look, the reviewers insist that we call it a pearl. We are very, it's very difficult for us to call our own work a pearl. So I think the compromise was that we called compositional verification a pearl and somehow got away in the title. But about a year after this paper was published, I met Igor Walukiewicz, who is a man whose taste I very strongly admire. And Igor had some, a word of praise about this paper. He said, I read your paper. It just read like a paper from the 70s. And because I know Igor, I know that this was a phrase of highest praise, that he could give. And maybe this is going back to Andreas's work, like many of these papers that he's been worked on and he has written feel like they're from the 70s. And I say this not as as a derogatory way, but I think it's really very elegant, very clean, and very readable. That's all I have to say. Thank you very much, and all the best.
Very quick question. I feel bad making you walk all the way here. When you say modeling, you don't mean that these are then the things that run in production or whatnot. I was a bit confused by that word.
So you should think of it as also the things that run. But the way of thinking about this is that when you start writing these distributed systems, you kind of use non-determinism as much as possible, right? You use this non-det and the assumes and so on to build the environment in which your code is running, right? And as you write more and more of the code, essentially what happens is that you have your actual messaging library, right? And think of this as a Rust trait, right? The Rust trait says, oh, here's a network trait that has a send and a receive and so on. So you can plug the must version in and out, right? So you just do conditional compilation to get something that the model checker understands and runs. And you could do conditional compilation to your actual RPC library, and that's the thing that actually can run in production, right? So of course, when you run in production, all these assumes and the non-debts go away with the actual things that you have in the environment. But the point is to have a very seamless transition between more abstract models where the state space is smaller and the actual implementation that runs.
So Rupak, there's something fishy about that sequential thing that you showed. What happens when the head fails?
So this is where I didn't talk about the coordinator. So the coordinator is essentially a Paxos cluster, and it's doing this kind of fault detection. When the head fails, essentially the coordinator will move it will find a new head, which is the next person.
Yeah, but what about the writes that are pending in the head?
The writes that are pending in the head, you see the head fails. These writes have never been propagated to the tail, and a write only finishes when it's written at the tail. So some writes can be lost. The coordinator has, there's a whole fault detection going on in the background, right? So you can think about the coordinator as, implementing a heartbeat or a fault detector and then doing a leader election to figure out who's the next leader, right? And the leader is always the head. So it is possible that there are some writes that never get acknowledged, right? And therefore they never show up in the replicated log. But this is true in a distributed system with message losses, right? So maybe the write didn't even show up to the head. Right? So the only thing is the consistency. If it gets written onto the tail, well, everybody will have a consistent view.
Hey, Rupak, it's been a while. So there was this system, what do we call it? P sharp, then it became Coyote. Yeah. How does it, I think Coyote was the latest version of this sort of stuff on the .NET side. How does Musk compare to that?
So I think any of these things you can do in any one of these things, right? So the language itself is a variable, the algorithm itself is a variable, but they're kind of independent variables, right? So one of our design decisions was to embed this whole thing into a language that can go all the way to production, right? And so this was part of our choice of using Rust, which of course brings to a lot of these things, because as soon as you get into Rust, well, what's your story about async and so on, which you can kind of abstract away if you're working in a nice, small language like P, right? On the other hand, then there's a gap between what you write and what you run. And this is you have to figure out where your tolerance lies, right?
Right, but my memory might be faulty, but I thought Coyote went to like C#.
Right, so the point is that, exactly, right? So if you think about the Coyote project, it again moved into this world where the code is actually C#. And it will again look at the send and receives as the primitives, and then build a model checker behind it, right? So in that spirit, you can think of Must as doing exactly the same thing, right? So there is a version, so there is some large systems code being written, there is a code abstraction, and then there's a model checker that explores the space of abstractions, right? So
you mentioned the paper on parameterized verification, but the number of clients is fixed.
yes, so this is stateless verification, right? So what we can take offline is, how can you take something like this and kind of go to a parameterized version, right? So now, and the main thing here is that the parameterization is the number of transactions that you run together, because in some sense, the length of the chain and so on, they're actually defined in the deployment, right? And it's usually 3, 5, I don't know, right? So that's not the hard part of the parameterization. The parameterization is, well, what happens if you have many clients writing to this thing at the same time? And well, okay, so one trick you can do is columnization, non-interference, and so on. So even with things like stateless model checking, you can actually go quite a bit far in doing unbounded proofs, right? But that's a separate talk.
And so if I may, I will add an anecdote, because you mentioned that we talked at LIX in Boston, and I remember this very well, because together with Sriram and Tom, we were working on what became this relative completeness of abstraction refinement. And I was stuck at one point, and I discussed it with you, and somehow you said, oh, this reminds me of an exercise of George Necula in the verification class. And we dug out that exercise, and there was the proof. I mean, the exercise was to prove a certain relationship between pre and post for deterministic updates. Do you remember this? And this saved me. Yeah. So thank you for this.
Since George is not here to defend his ideas, I will take credit. Yes, of course.
But it also shows the virtue of exercises, right? So I mentioned the one that you observed.
Right, our next speaker is Lenore Zuck. She's a professor in Chicago. She's, as far as I understand, a long-time comrade and collaborator of Andreas. PhD students have been exchanged, and yeah.
I'm not a collaborator. I'm a long-time friend. We never managed to collaborate. We had lots of discussions, lots of arguments. God, we're good at arguing. I can just give a list of arguments. So, because Rupert said that we need to talk on work on. Oh. God, that reminds me the first time I saw William Paul de Roover with a microphone, with it like in his hand. He started singing. I'll spare you. So I told that I needed to work on distributed systems, so I just immediately did it during Rupak's talk. But people have brought presents to Andreas, and so I thought I should bring him some present. So here is one present. And then there was a discussion about dogs, and Penelope felt really left out, so she wanted to join. And then I thought maybe that wasn't enough for a gift, and we have Dirk here who knows how to preserve things forever. So I added a bottle of wine. We'll get back to it. But as I said, I've known Andreas for decades, and one of the things that we started discussing and probably arguing, I remember some arguments about it, is liveness. And it was like, people think that liveness is not necessary, but we don't believe that. And eventually, together with Bernhard, we organized a Schloss-Ringberg seminar that some of you were in. And if you remember, we asked for liveness manifestos before. And people wrote things that range from really, really smart to really, really dumb. And Andreas's was that the issue that is of liveness becomes obsolete once we have shown that good methods for checking safety are in fact methods for checking liveness. And we're working on it. And we still are. So here we go. By the way, this is one at least URL where you can find the material for the workshop, some really nice writing by several people about liveness and what they think. And I think some of them would have changed their minds by now. But it's been 20 years. So I'm going to talk about, well, not really mechanical, but I'll pretend it is, verification of liveness of distributed systems with arbitrary topologies. And It's really hard because we're trying to avoid induction. Our induction is really not very nice for mechanical proofs. And the current approach is strict the topologies, makes it easier. Things are very symmetric and nice. And how are we going to do it? We're going to model systems as parameterized systems because that's what we know how to do. I mean, we who are standing here. Then we'll reduce liveness to safety, and then we use safety methods because Andreas told us to. And we're obedient. So let's just take the progress property, the most general liveness property. Always P implies eventually Q, or the double arrow is for entails. P entails eventually Q. So whenever we see a Q, a P will eventually see a Q. Let call every state that starts that originates from a P that is on a path that has a P state and that hasn't satisfied Q. Let's call it pending or pend. So I'm going to kind of fix P and Q and pend. And I promise you, there are not going to be lots of Greek letters here, but just a few. So we want to show that a system S satisfies the psi, and we can't do it without fairness because fairness is what gets the word going. We must have something moving on. And we're just going to use justice because it's easier. And it's better for a talk and stuff. And justice just is like what others may remember as weak fairness. It just said that some state assertions must be satisfied infinitely many times. Give the set of state assertions that must be satisfied infinitely many times. And deductive proofs usually depend on some well-founded ranking. So the idea is to come with well-founded ranking and to show that this well-founded ranking monotonically decreases over the pending states. And that also with each fair state, it strictly decreases. And that is the nature of most of the deductive rules for liveness. And since it's well-founded, you can't fall off the floor, you're bound to have fairness infinitely many times you decrease, and therefore you reach your goal. But that actually indicates that liveness is bounded by fairness. So even though we're not saying it explicitly, we are bounding the liveness by some occurrence of fairness properties. And that provides us the bound. And this is the bound we can use for safety. And I have two more non-picture slides, almost. So here is one of them. The idea is to have a planar. So a planar is just a sequence of justice properties. So a finite sequence of justice property, let's call it sigma. And the idea is to let a planar for liveness property psi will just track the just. So it's a sequence of justice properties. So we're just going to track when the first one occurs, we mark the first, we wait for the second, we wait for the third, until what? Until we exhaust the planar or we reach a Q state. So, so that, in fact, this sigma is a bound on the safety, on the liveness, and it is allow us to translate liveness to safety. It is exactly the transformer we need because we can express the sigma as a non-interfering monitor. So one thing that is not very convenient is to have those fixed sequences. So sometimes I want to say, let any process take a step. Like I want each of the processes to take a step. I don't care which order. So I don't want to come with n factorial combinations of these planar. So I'm allowing parallel operator in regular expression. So A parallel B is A, B, or BA. So that just allows me, and then if I have a set of justice properties and I, which is just a subset of the justice properties, then a planar would also be any combination of these justice properties, any parallel combination of these justice properties. I'm usually using it when I want to let everyone take a step. And I can take a planner and apply it k times from a constant k. For example, everybody schedule once, and then everybody schedule again, and then everybody schedule for the third time. And this is how I extend the planner. Non-interfering monitor, so now if I have a planner, a non-interfering monitor will just track the planner, and it will start working from a non-pending state, assuming it's not operating already. It will track the planner, and then either we reach Q, and then we show that Q is that psi holds, or we don't reach Q, which means we got the wrong planner, or maybe the psi doesn't hold. But if we can show that whenever we reach sigma, psi holds, then we're done. This is a safety property now, because now we bound it, which says like, we're waiting for sigma to happen. Why are we sure sigma would happen? Sigma is just a finite sequence of justice properties. Doesn't matter how exactly I expressed it. Every one of them is bound to occur infinitely many times. They can occur in any combination, in any order infinitely many times. I'm just waiting to exhaust them, and then I'm done. Okay, from here on it's examples. And process mutual exclusion with dumb semaphores. That is not semaphores, because then I'll need strong fairness, and I don't want strong fairness, I want justice. So it's and process mutual exclusion with a dumb semaphore that doesn't guarantee individual individual liveness. So it's just like this old protocol that's just like the example on which I try everything and on which I try every one of my ideas, and most of them fail at this point. Here it succeeds actually. So and processes, there is this what I call semaphore T, which is a dumb semaphore, and everybody starts like in a non-critical location 0. The wait for the T to be available, and then they take it. T can be, well, let's call it token. And then when they take it, they set it to 0, enter the critical section, leave the critical section, and return the token. The liveness property, this is a really weak liveness. It says if there is a process in location 1, then eventually there will be a process in the critical section. That is, if somebody is trying, then somebody will succeed. So that's a price I'm paying for not having strong fairness, but it's also just real basic example. And it's also topologically not interested. This is a click, so it's not. So there are 3 justice properties for each process. A process cannot be stuck forever in location 1 when the token is available. And a process cannot be stuck forever in the critical section, and a process cannot be stuck forever after the critical section. That is, the only thing that we allow is a process to be stuck forever at the non-critical section. We don't force it to want to enter the critical section, or it can be stuck if it's in location 1 and the token is infinitely often not available. Then it can be stuck. And what is a planner? Wow, this is a planner. Schedule everybody 3 times. So go to 3 rounds where everybody schedule once. There could be some other planners. Actually schedule everybody 3 times would have worked too. There are lots of things that we can do. Why 3? Because suppose when we start this game, there are processes waiting at location 1, but there is one process at location 2. We need to schedule everybody once for the process in location 2 to go to location 3. We need to schedule it again. So we need to schedule everybody because we don't know who it is. Again, to get it out of location 3, and then we need to schedule everybody again to make sure that the process in app process in location 1 gets to location 2. So this is the planner. Okay, this was really easy, so let's move to a more interesting example. Spanning tree is it's a somewhat simplified version of the spanning tree from Nancy Lynch's book on distributed systems. We have a graph, G, which is bidirectional, and each node is a process. For a node V, neighbors of V just imply the neighbors that are directly adjacent to it. And we're going to have a designated node, which is a root. And we're going to build a spanning tree from that root that is rooted at the root, at V0. So V0 is a root, and we're going to have three auxiliary structures. For every node, which is, for every node, we have a parent, which is V or bottom. Bottom means it doesn't have a parent. The root will not have a parent at the end. And initially, it's bottom. We have a latex arrow here, and on top of that, a variable done that is true if and only if the node is not a root. So if the node is a root, that is done is false for everybody but the root. And a matrix ping, which is a Boolean matrix that is only has one in the V0 row for V0's neighbors. Okay, so here is the algorithm. Now it fits in one page with all those shorthand. So what we do while a process is not done, if it doesn't have a parent but somebody pinged it, it chooses one of those who pinged it to be its parent, and then it goes for every one of its neighbors and sets ping to true, and then it's done. Justice, every process takes infinitely many steps. Okay, let's look at a run. Suppose this is our graph. Initially we have a root. It sends ping to both its neighbors, and the first one to get it sends ping to its neighbors, and we end up with a tree. And there's only one mistake here that I noticed. But these animations are so annoying, so I'm not trying to fix it, because you didn't notice it. So that's how we get a tree. So this is the protocol. And what do we want to show? That every non-root parent eventually has, every non-root node eventually has a parent. So what we're going to do is we're going to schedule everybody n times. That is, and the reason I used n and not cardinality of V is for two reasons. One thing, cardinality of V really looked ugly. For some reason I couldn't put PowerPoint, and LaTeX did not collaborate with me on this one. And also because I want to make sure that I'm not using really cardinality arguments here, that I'm looking at n, at the number of processes. And then once a parent is done, once a node is done, I just need to schedule it for every node that is not done, I just need to schedule the number for its parent for it to be done. Sorry, once it has a parent, I need to schedule it this number of times to be done. So that will do for this one. And I'm going to just kind of let you see and not see this comment. If you lost it, who cares? Last known example, but it's really fun, is my Klube's maximal independence set. And so we still have the same graph, but we're trying to choose a maximal independence set. A maximal independence set is a set of nodes. So if a node is in the set, none of its neighbors are in the set. If a node is not in the set, it has some neighbor in the set. So that will be a maximal independence set. And as I said, the protocol is due to my Klube's, and it's kind of old, and it's synchronous, and it's probabilistic. So I'm not going to get rid of the probabilistic because, you know, guys, I love probabilities, but they're just going to make them very simple. And but I don't like synchronicity, so we're going to do what we usually, because our models are asynchronous, so we're going to use asynchronous as synchronous. So the rough solution is that the solutions, that processes go in rounds. There's rounds. Each round consists of 3 steps. At the first step, everybody flips a coin. So we're going to let it flip a coin high-low with equal probability. real protocol, they can be other values too, with not equal probabilities, but all bounded from below. So what I say still holds. And so it flips a coin and sends the result to all its neighbors. At the second phase, it assembles all the results. And if it drew high and all its neighbors drew low, then it says, I win, and it sends a winning message to all its neighbors. At the third phase, if a node receives a win message from one of its neighbors, it loses and it withdraws. So you can stop playing if you win or if you lose. And then you drop out of the game and you don't play anymore. And the playing nodes continue the game. Okay, the graph. So we start here that everybody's in phase 1. Let's say that some nodes drew low and this one drew high. Note that those who drew switch to phase 2. And note also that even that this one has a high neighbor, it cannot tell that it lost it because it has a neighbor that hasn't flipped yet. So we have to wait for this. So now this node notice it's a winner because both its neighbor lost. So it is a winner. So we know that these two will lose, but it's too early for them to lose. So they cannot admit that they lost. They know it, but they can't admit it. Isn't that a problem of our life? Then these two draw high. Again, this has neighbors that drew low, so it can be a winner. This has neighbors that could draw low, and I was just like, so we have 2 more winners. But now some of the losers that couldn't lose before can lose, so we just get rid of them, kind of. And then, let's say that we're left here. So why is this interesting? Because here we have 2 nodes that are in phase 1. If they both draw high, nobody will win. If they both draw low, nobody will win. The only way we'll get out of this bind and not end up in infinite loop is that one would draw high and one would draw low. Fortunately, probability theory, or measure theory, tells us that that's going to happen with probability 1. So we're proving liveness. We're just proving progress. We're the gods. We tell the coins how they should end. So we're going to tell one to do high and one to do low. And then we can terminate. And this is a maximal independent set. So why it's a maximal independent set? By the way, why the previous thing was a spanning tree? We live to life. It's a safety. This is a safety proof. Here we only care to show termination. But here we have 2 types of termination. One termination, so we want to show that every node eventually stops playing, because once it stops playing, it's a winner or a loser. So we want to show that eventually a node is not playing. Okay, I think I messed up this notation last night. Let's consider the set of playing nodes. So we need to show how we're going to get there. So a simple planar, the one that we talked about before, shows that eventually everybody takes a step, and therefore we can show that everybody eventually draws a value. Now we need to get more sophisticated to tell them what to draw. So the previous solution showed that eventually everybody draws. So we're going to do a probabilistic planar that tells them what to do. And as long as this planar is finite, we're bound to occur infinitely many times probability 1, so we will win our case. What should we do for this? Actually, there are lots of ways of doing it, and some are better than the others. Here is the dumbest and simplest one, and that says, let there be n lows. followed by one high, followed by n lows. Somebody's bound to win. Repeat it n times. Each time it happens, somebody's bound to win. You're done. That is actually a rather complicated planner to do. So it may be very difficult to accomplish. So we can do some other things. For example, let the first one who is playing, the first playing one that needs to draw, let it draw high and everybody else draw low. So that's kind of faster. Or let somebody draw high if and only if nobody in its neighborhood drew high. So that's even faster. And it is better than others for other considerations. It will be easier to implement. So we have lots of other possibilities. Okay, some notes. As I said, the original protocol is synchronous. The choice of probabilities are not fixed, either bounded from below. Why do I keep saying bounded from below? For me to apply any reasoning that a finite sequence must occur infinitely many times, I must have this bounded from below. So I keep repeating that this holds. Mike Luby's goal was very fast convergence. We're only caring about convergence. We're just showing liveness, not very fast liveness. So we may as well use high-low with probability half. We have nothing to lose because that's all we want. And I'm done, and I was really fast. So, last slide. Yeah, it's got the title last slide. It must be the last. Actually, I cheated one before last. Who cares? Bounded safety can almost always replace liveness in distributed protocols. The bound is a finite sequence of fairness conditions. As I said, we may want to express it in different ways, but it is a finite sequence. We have a family of finite sequences, one of them should hold. It's very similar to ranking, but it's actually much simpler to mechanize. And it can be extended pretty much the same way to liveness with probability 1. Some things are better left unsaid. That's it. Let me return to my gift for Andreas. Remember this bottle of wine? I want you to see its price. But I also want you to know that this is the small version. I didn't get him the full bottle. So, I'm done.
Replacing liveness with some notion of finitery, or with fairness with finitery fairness. Is that what allows you to have a reduction to safety? Because in general, there's a computability theoretic reason why you should not be able to do this, right?
Yes, that's exactly it. But I'm saying that in most cases, and in many of the proof rules we use for parameterized, when we do liveness, liveness with all those crazy things that we've done, we always use fairness.
But finitery.
Finitery, yeah. And I'm not saying that that covers all bases, but I'm saying that in most cases that's enough. Not in all cases. I can definitely come up with cases when it doesn't hold.
Someone? No?
You really resent the small bottle, huh?
Thank you very much. Okay, our next speaker is Jochen Hönicke. He is the main author, I think it's fair to say, of SMT Interpol. He's been on many, a co-author on many papers we've seen during the talks today. He's essential for example, my PhD thesis. And when Lenore showed something and then said there was a mistake and then it was gone, I looked at Jochen. Maybe he saw it.
It was a mistake.
You didn't?
No, I thought she just does not dwell on it. I just didn't want to. Andreas taught me this lesson. That some things should not be highlighted.
So whatever it was, we leave it unspecified. I'm guessing Jochen saw it.
I didn't see it. But
it was called reachability.
Yeah. Yeah, this is another paper which is a collaboration with Andreas. In this case, it's with Oded and Sharon from Tel Aviv at that time. And this is actually work that we did with Andreas, I think 7 years ago. And yeah, we left some question open in the paper, and this is about answering this question finally after 7 years. So the paper is about another safety to liveness reduction. So again, I think we have just seen it in the paper, in the talk before, that there are these properties, safety and liveness. And in some sense, you can prove liveness also with safety. And the safety property is basically a bad thing will never happen. So it could be an invariant that something is always true, so it's never wrong. While a liveness property is a property where we say something good will always eventually happen. So it's, for example, termination is a typical example. You want your program always terminate. And there's basically this always eventually is a quantifier alternation. So it's not enough to just have one witness. For safety, it's enough to see a bad behavior and you know there is bad behavior. For liveness, you don't have a witness because it could be that the program has just not yet terminated. Or it could be a terminating run, but then you don't know anything about the other runs. So liveness is a bit more difficult. So for safety, we have good tool support and we can handle programs with infinite states, with invariants. For liveness, there's only limited tool support and most can't handle infinite state. But there is an exception. So there was already before us the work with Andre and Byron about these what they call transition invariants, where we prove an invariant not for one state but for a pair of states, and then we can use ranking function to prove that the program will always terminate for infinite state. And this is what we started with 7 years ago with Oded, and we wanted to apply this technique for distributed protocols. And yeah, we wrote a POPL paper published in 2018. And yeah, this was called Reducing Liveness to Safety in First Order Logic. So we applied the technique. We actually ended up with a slightly different solution, which didn't even require ranking functions. But we weren't so happy about it because there were some there was something called nesting, which was a bit ugly in the formalism, and we had some problems that we couldn't solve with this, even though it should be possible to solve them. So already half a year later, we came up with a continuation of this paper where we used temporal prophecy for proving temporal properties. So it's another very similar liveness to safety reduction, which got rid of the ugly nested thing that we had before. But still, the reduction is, of course, not complete for infinite state system, and this is an unavoidable problem because liveness is more difficult than safety. You can basically prove it's a different decidability class. But the question was, does it solve our problem? So we had the problem that we couldn't prove the termination of the Ackermann function. With arbitrary nesting, even with arbitrary nesting, it's not possible. So in the first paper, we actually used this as an example to show the limitation of the method. We said, doesn't work. And for the second publication, we tried to prove it. And then the deadline was nearing, and then we had to publish, and there wasn't any space anyway in the paper for a proof, so we left it open and we didn't even mention it in the paper. So this paper is now about the answer to this problem. Yes, we can actually prove it with the same formalism that we had in this paper 6 years ago. So I want to basically explain the technique that we used. So to start this, we need to say what are our systems for which we want to prove fairness properties. And in this case, we wanted to have a powerful mechanism to prove distributed systems. So our base logic is first order logic. And then we have fair transition systems over first order logic, where we describe the initial states by a first order logic formula. We describe the transition relation by a first order logic formula that talks about a primed and an unprimed variance. And basically the variables are now predicates and functions from first order logic. So you can think of the predicates of first order logic as one state of the system, and if the system evolves, the predicates change their meaning. And then we have a set of fairness constraints. It's a finite set of fairness constraints, but each fairness constraint is a first order formula with 3 variables, so it can actually describe a set of infinitely many fairness constraints. And to make it more practical, I used an example that Andreas will know, which is the ticket algorithm. It's a very simple mutual exclusion protocol that you have seen in many supermarkets already. So you want to enter a critical section, like you want to get your meat from the supermarket. So what you first do is you draw a ticket from a ticket machine, and this ticket machine will give you a number, and it will automatically, when you pull the tickets, increase the number so that the next customer gets the next highest number. And this is here modeled by a global variable t. And if you draw a ticket, it's copied to your local variable m. So we have one local variable m for every process. And the t is automatically increased. And then you wait. You are in the queue. You don't have to queue up because you now have the ticket. And there is a global variable s, the service number that is usually posted above the counter, which tells you when it's your turn. So you wait until the number s is greater or equal to your ticket number. And if everything works, it should be equal. And then you enter the critical section. And when you're done, you leave the critical section, and you should also increase the service number to let other people in. And this is the whole algorithm, and we can describe it. So we have the global variables, which are just constants in first order logic. We have the local variable which is a function from process number to natural number, so we use functions. And we also use predicates from process ID to bool to describe our program counter. So you can think of this as an infinite thread system where we have infinitely many copies of the thread, and they all run in parallel. Yeah, and then you describe the initial state by a formula. You describe the transition predicate by a formula. Here you use a primed and unprimed variable. So you say, for example, if you want to increase t, you say that t prime is a successor of t. And you also have to mention all the variables that don't change. So here it's also important we can use quantifiers to express that one process does the step. So x is the process that does the step, and all other processes don't change the meaning. And then we have the fairness properties. For example, we want to say that we are not infinitely often or not in C. So this basically excludes the traces where we stay in C and block everything, and we want to avoid, we want to forbid these runs. And then other fairness property tells us if it's our turn, we must leave the waiting state. Yeah. So the next thing that we need is what is a fair run of our system, what is actually a run of our system, and we call it a fair run. So a run is what you would expect, a sequence of states. And these states are all first order structures. So these are basically valuations for all the functions and predicates. The initial state should satisfy the initial formula, and every pair of states should satisfy the transition constraint. And the fairness constraint tells us that for every fairness constraint and every possible valuations for the free variables, the x in this case, we should see infinitely many states that satisfy this fairness constraint. Then we need another thing, namely the property that we want to prove. And for this, we use first order linear temporal logic, which is basically first order formulas extended by linear temporal logic operators. In this case, we restrict ourselves for simplicity to this eventually and globally operator. I think you all know what this means, and I don't need to explain them. And then we can express the property for ticket as a first, sorry, this was too fast, as a formula where we say, for all processes, whenever we are in the waiting state, we will eventually reach the critical state. So now we want to prove this, now we want to show that this property is true. And since we only know from Andreas how to do termination, the next step is to basically reduce the whole problem to termination. So this is done with a monitor automaton. So we basically have an automaton that monitors whether this eventually f holds or not. And it's kind of tricky because it guesses non-deterministically whether it holds. And if it guesses wrong, then it will not succeed and we don't have a fair run. But we can show that it can always guess right. So basically this monitor automaton doesn't restrict the possible runs if it always guesses right. And the transition relation just is depicted here. So we can start in any state except the state where we have f, but eventually f doesn't hold, because this is a state that is not possible. Eventually, the finally f formula implies that f should, if not finally f holds, then globally not f holds, so not f should always be true if this not finally f holds. And then it can do arbitrary states changes, but it cannot basically recover. Once it's in this not finally F state, it can never go to the finally F state again. And then we have a fairness condition that it shouldn't stay in this rightmost state forever. And this is all we need to produce a monitor. And then we can show that our original system satisfies the fairness constraint if and only if this monitor plus our system has a fair run, has no fair run. And no fair run basically means it always terminates because our fair runs are infinite. So how can we prove termination for the systems? And this is, this is the main idea of this. We don't want to use ranking functions in this case, or Oda didn't want them. He didn't like them, and he said we can go without them. So if we have a finite system, we just look for we look for a so-called lasso. So we have this observation for a finite system if it has no fair run, if it has no fair lasso, and vice versa. If it has no fair lasso, there's also no fair run. In this case, so a lasso is some path that ends in a cycle. So it's like a cycle, except that the cycle doesn't go back to the initial state. And a fair lasso is a lasso where the cycle has a fair state. Basically, it fulfills all the fairness properties. And this works well for finite systems, but for infinite systems, we need to come up with a solution. And our solution was use a finite abstraction for infinite state systems. And it's a one-way thing, so if you have an infinite state system where you can show there, and you have a finite abstraction that doesn't have a lasso, then you know it will always terminate. But it depends on the abstraction, and if the abstraction is too coarse, then you have spurious finite lassos. And you can't just say if there is in the infinite state system a lasso, no lasso that it's terminating, because an infinite system doesn't have to go into a cycle in the end. It can, for example, increase a variable indefinitely. So how do we get a finite abstraction? And this was the key idea here. Just do it automatically. Instead of considering the system and looking what we need, we basically want it depend on the current run. And the idea is to run the system for a while and then look what did the system touch. And if it ran for a finite amount of time, it should only touch finitely many elements. And if we restrict our view now to these finite elements and say every state that coincides on these elements is basically a cycle, then we have a finite abstraction. So this is the core idea. What we now need to do is to find these abstract lassos by a monitor automaton, and then we have reduced it to safety. We basically want to say if we reach the error state, then we found a finite lasso. So we reduced liveness to safety by adding this monitor automaton. And this automaton works as follows. It first looks at an initial footprint, which is basically all the initial state and some maybe some important objects that we need. For example, the thread that we are looking at that will get stuck. And then we wait until the fairness constraints are observed the first time, and then we fix the abstraction. And then we search for a cycle. So at some point we decide this is the start of the cycle, and this is a non-deterministic step. So we ask, is there a run of this monitor automaton? And when we save the state, we save it to a temporary variable, or to this variable as 0. Then we wait again until we see all the fairness constraints that are now in the footprint. And if at some time where we have seen all the fairness constraints, see a cycle, then we have an error. And how does it work for ticket? Well, we assume we want to show this property. And the first thing is we build the monitor automaton. We negate the formula and assume initially that it doesn't hold. Then, yeah, because it's an existential quantifier, we can fix the x0, which is a witness for the process that isn't treated fair. Then we add this process to the initial footprint, so our fairness condition will now ensure, because it's finally, that it will happen when we reach when we leave the first waiting state. So we basically wait here for the finally to eventually happen. And then we have we know that the process is waiting. It will never be critical again. An important thing to note here is at this time, we know that we know all the processes that are in the queue before this process that we looked at. So we have already seen them, they are in our footprint, and we can reason about them, and we can reason about the ticket numbers. So when we later enter the safe state, there must be one of these processes that has the right, that is either already critical or that has the ticket to enter the critical state next. And so when we enter this safe state, there is a thread, and once this thread does a step, we are already proved that we don't have a cycle, because he will enter the critical section or leave it, and then he is no longer in the queue, and he will never be in the queue again, because even if he re-enters, he gets a higher ticket number. And the important thing here is that the x0 must be in the initial footprint. And we call this the temporal prophecy witness. And it's kind of, interesting that you can do this. You can just assume there is a witness for this existential quantifier, if it's true. And then take this witness and put it in the initial footprint. And by putting this witness in the initial footprint, it will delay the time when we reach the abstraction, and it will automatically refine our abstraction to be to be fine enough to prove the property in the end. Yeah, and the temporal witnesses also uses these LTL formulas. So we use additional LTL formulas in our proof, and we also build basically the monitor automaton for them, and then we can use the invariance in our proof as a safety invariant. So our proof basically states the LTL formula, and the monitor automaton will make sure that the LTL formula corresponds to reality. So how do we prove Ackermann? So yeah, Ackermann is this function. You have probably seen them. It's undergraduate topic for us. It's a function that is remarkable because it grows very quickly. It grows quicker than any primitive recursive function. You can't compute it with nested for loops. And this makes it tricky. And this is the reason why we couldn't prove it with the original formalism. And if you want to express a ranking function for it, well, you could use the Ackermann function itself as a ranking function, but then the proof is cyclic in some sense. So the other way is you use simpler ranking functions that only take m and n, but then you need something like ordinals up to omega to the power of omega to express your ranking function. And then you can use lexicographic ordering on natural numbers and prove that these are lexicographically descending. And this is also the reason why we didn't want to use ranking functions, because it's so hard to come up with them. Yeah, we can model this Ackermann in our first order logic. We need a stack for this. So if you have this recursive call, you push the first argument of the outer call to a stack. So you remember to do it later. And then you you continue with the inner call. If you are in the step where you don't have a doubly nested, but you basically the second case where a of m plus 1 comma 0 is a of m of 1. This is basically tail recursion. You just continue with the new m and n. And the last step is where you return the value, and then you need to pop the last element from the stack and use this as a new m. So we can write it as a system in Ivy. This is somehow Ivy syntax where we have these 3 steps. This is a pop. This is a step where we just change m and n, and here we push a new element to the stack. And then we have the finish step where we are basically done. So if the stack is empty and we are at a0n, we can return the result. Then we want to prove that this terminates for all possible inputs. So what we then need is some function that generates all possible inputs, and this can be easily done by by some actions that only run before Ackermann started. So they assume not started hold, they increase m and n arbitrarily, and at some point the start action happens, and then we set started to true, and yeah, we also remember the m and n. And what we want to show is, as a temporal property, whenever we, for all states, if we start Ackermann, then we will eventually finish. And yeah, this was what we didn't manage 6 years ago. So this is basically the solution for this. The first part is easy. We need two prophecy witnesses. One is the M0, which is basically the M0 which we start with. And this is an important constant that we need to talk about. This is basically the iteration, the nesting count of the Ackermann function. But we also need, and this was the tricky part, to distinguish. We want to say if there could be the case that we run into an infinite loop, and there could be the reason could be because we pop infinitely often something from the stack. And if that is the case, we want to know the largest number that we pop infinitely often from this from the stack, and this is our prophecy witness. So assuming that the existential quantifier holds, this prophecy witness should have the right value, and we add it to the footprint, and this works. And yeah, the basic proof is a k-split. I don't want to go too much into the details. So one case is we don't have infinitely many steps where we pop from the stack. And then we know that there is some time where we never pop from the stack again, and because of fairness, we know that this is already happening when we freeze our abstraction. So when we reach the freeze point, step 1 will never happen again, and step 2 and step 3 can happen, but they don't increase m and n. And this is a property of Ackermann that, well, here m is decreased, and here m stays the same, and n gets decreased. So there is no, so m and n will always stay in the abstraction, and then we can easily reason that there is no cycle, because m decreases, or it stays the same and n decreases, and we see everything in our finite abstraction. And the second case is there are infinitely many steps, and then we actually need to prove by induction that there is a maximal one. And then we know from our witness that y0 is the maximal one. And then we know that after the freeze point, we already are in the state where where all smaller ones are not, no, all larger ones are not taken anymore. And then we can argue that because the larger values are not popped, that then we have a finite number of m's on the stack, and when we pop it, it will never be pushed to the stack again. We can prove this, and then we run out of m's at the some time, or of these y0s. Yeah, tricky proof, and there are some details that make it even trickier that I don't want to go into. This is basically what we need. But if we add this to our automaton, it's already an automaton that doesn't have any cycles, any fair losses. So it's interesting that what we couldn't prove in the first paper works if you add these temporal witnesses. Yeah, so I want to conclude this is basically the liveness to safety transformation. We did this, Andreas, 6 years ago, and it works for infinite states. It can handle even this Ackermann function, and this is a new result. And yeah, it's an elegant solution because there is no the only thing that the person who wants to use this mechanism needs to come up with is finding the prophecy witnesses or defining them, but he can use arbitrary ones, and then he gives an invariant and proves it with safety. Thanks.
Hello. So I just want to, because until which degree you automatize this? Because once you use LTL with the first order quantification and all these things, so I'm not quite sure about automation after that.
Yeah. So we actually use Ivy for this. So our restriction is that the first order logic are in EPR. So this is you restrict the quantifier alternation. You have existential quantifier on the outside and universal quantifier on the inside, and you restrict the functions. You can't have functions from int to int, and this is also why we model the stack as a predicate. And if you do this, then the logic is decidable, and the LTL is just a monitor thing. So it doesn't, it's just, what you do is you just add this formula to your transition relation, and that's it. The tricky part is, of course, to use in the proof. In the proof, you need to reason about the fairness constraint here, and then basically reason that if you reach the abstract state, you are already, if you reach the state where you freeze the abstraction, you are already in the state where this property now holds without the finally operator in front of it. And it's fully automatic, so except that you need to write the invariant manually. So you write the invariant manually, you mention the prophecy witnesses that you want to use, and then the tool will check that the invariant is inductive, and if it's not inductive, it gives you a counterexample, and you can think about it and fix your invariant, and if it's inductive, then you know that your program is correct.
Okay, I just want to understand. You said reduction to safety, and safety is because you look at these automata and then ask for reachability, or
Yes.
what?
So the thing is, we know that there we know that there is the fairness property is violated if we reach the error state, or is possibly violated. It could be because the abstraction is too coarse, that it's a spurious violation. But if we don't reach the error state, we know our program will terminate. And so we check reachability of this location.
Thank you again. I think we'll have coffee now.
Right, welcome to the last session. We'll start with Byron Cook, VP and Distinguished Engineer at AWS, where he gave food and shelter to a lot of us in this room, and he gives us shirts. He has been there for coming up to 10 years now, almost 10 years. Before that, he was at Microsoft, which we had already working on termination proofs with Andreas, which was basically the reason why all the PhD students in this room didn't see Andreas in Freiburg, because he was always in London working with Byron. So I'm looking forward to your talk.
All right, great. Thanks very much. Thanks. Martin encouraged me to submit, and he said, submit something that's beautiful, but maybe not very useful, right? It doesn't need to be useful. Just make sure it's beautiful. So we've been to this thing. I think it's potentially quite beautiful. I think that there's some structure, Andreas, that you'll enjoy. I also think that if I'm right, it'll also be disruptive, and I know you like to be disruptive and troublesome. So that should appeal to you. Okay, sure. Sure. It's also, there's some, I think you might see and enjoy some similarity and outline to your prior work, which I think was also very disruptive to the conventional wisdoms at the time. So that led to this Scientific American article about the work. There were many papers where this, I have a picture of you, Lenore, yeah. So 2004 at ETOPS, apparently, according to the internet. Yeah. So where I first met Andres was at ETOPS in Barcelona, where I didn't know Andres when he was at Microsoft. We missed each other, but then I told him I was going to be moving to Europe. So then he encouraged me to come to the Schloss Ringberg workshop that Lenore mentioned. So that was that's right. Okay. Anyway, so we had very good discussions. I was invited to come to Saarbrücken and work with Andre, and that's kind of where the magic began. So then we I didn't co-chair very well, so I did co-chair VMCI. And we met in Paris quite a bit. Those were, I think, really amazing times in London, Paris, Germany. So thanks very much. So that's the end of the gushy bit. So let me tell you about this work that we've submitted. I wanted to tell you a bit about the motivation. I'll probably spend about 10 minutes there, and then I'll give you an illustrative example. The details are in the paper, but the high level is that we're distributing SMT solving. We're getting pretty exciting results distributing an SMT solving, and that raises the question of whether or not we could or should be doing something different with regards to quantifiers. So as you may know, Amazon is a big investor in automated reasoning on formal methods. It's important to enterprise customers. We have a number of customer-facing features. Billions of calls per day to the solvers. We've done proofs about a bunch of open source code, from FreeRTOS to the encryption SDK to something called AWS libcrypto. And then we're doing lots of proofs internally to Amazon. So practically every bit of code is either directly or indirectly touched by proof these days. So all services use networking, virtualization, storage, cryptography. We're doing, in some way, we're doing proof about all of those pieces, and then everything's kind of built on top of that. Under the hood are automated theorem provers. A couple of years ago, we launched something internally called the Amazon Trusted Solver. And this is a cloud scale service. So I'll just show you kind of what it looks like at the command line. So you could call it like CVC5. Here I give it a file, and then it gives you an ID that then you can do various things with, right? You could ask what's the status of it. You could kill the job. You could do all the things you could probably imagine. You can also set up different solver configurations to like race them, for example, so you can compete, or you could run them in a way where you get the results from both of the solvers and then make sure that they give you the same answer. And so this is it began its life when a service team in AWS that was building an automated reasoning based tool used Z3 with a flag that everyone knew was unsound, right? If you talk to the developers of Z3, you knew the answer wasn't right, and it caused a very bad day for a bunch of people. So we realized that we needed to wrangle the usage of solvers into a more central place, such that we can make sure that people were calling it correctly. But we've also learned that it's great for using this style is great for collecting telemetry and helps us make decisions about where we're going to invest. But then also the really amazing thing is it helps facilitate the move to distributed proof search. So I'll say a little bit more about that. So here are the provers that it currently supports. And if you're a prover solver kind of person, you probably know all of them. You may not know NFA2SAT, but that's not really the point of this talk. The point is about this one. So the A4 is sort of a code name for a distributed solver. And the question is, can we meaningfully distribute solving across thousands of machines to improve the latency? And we're really inspired by this work of Malab Mono. So hold up your hand if you know Malab. Yeah, so not many people. This is like, I don't know, this is like, it's a real game changer. So to give you an illustration of how amazing this is. So this is a graph you've probably seen before. This is all, or some version of this. This is all of the winners of the international SAT competition from when the SAT competition began until 2020. And they're compared on the same hardware and the same benchmarks. So you can see over time, the solvers are getting better and better and better. Okay, and then to read this, I mean, hold up your hand if you know this kind of graph. Do I need to explain this graph? Yeah, I'll just say a couple words. So here, this solver at the top, this is saying that there's about approximately 250 instances that could be solved in 200 seconds. So that's better than this solver, which can solve only about 100 benchmarks each under 200 seconds. You want to be on the top, not the bottom. And right, so I said that. So this is basically 20 years of progress in SAT research, and then this Malab Mono is this new distributed solver, which just blows away 20 years of research. Now it uses a lot more computation, right? Because you're using many solvers. So we've moved from a sequential to a distributed solver. So definitely this is not an apples to apples comparison anymore. But basically this new distributed solver class gives you a new capability that you really didn't see before. We're also seeing similar results for SMT. This work is considerably more preliminary, so I won't go into the detail. So just a little bit of details on how that works internally. So this sort of table stakes idea of distributing solving is just to use a portfolio. So this is this compete mode where you just run multiple solvers, perhaps with multiple configurations. So imagine you have some file F and you want to pass it to a solver. You could pass it to one solver, or you could pass it to a whole bunch of solvers. Maybe you seed them all with slightly different numbers to kind of get them into different states, and then or you could shuffle them. But basically, the horizontal scale gives you more chances to succeed. That's the idea of portfolio. But then what you can do, and this is what Malab Mono is doing, is you could share the conflict clauses between the solvers. So basically the lessons learned. And it's something like, I don't know if you've ever done, like you've sort of these group exercises where you have small teams all trying to solve some sort of puzzle, but they're in the same room together. And they can solve, someone in that team will be able to solve the problem faster because they're learning they're seeing that the other teams have some method they're using, they're getting a bit of success with, so that you can basically copy the ideas from the other teams. And it's the same idea here, that you basically have the solvers running independently, but they're sharing the lessons learned. And there's a bit of work to decide on what to share and what not to share, and when to share it and so on. But it's a good idea overall. And so one of the things I really like about it is that basically good decisions pay compounding interest early. So imagine you get a good decision, like a SAT solver decision here. Then because the learnings are shared, you get to the good decision 2 sooner. And because of that, you get to decision 3 sooner, and 4 sooner, and 5 sooner, et cetera. So there's more opportunities for good decisions in this distributed environment. And furthermore, the bad decisions don't cost you as much. So imagine that we had a few solvers that ultimately didn't contribute anything to the final answer. Well, that's no big deal. We just throw them away. So when I Google German prison cell, this is the photo I got. So I'm using this as an analogy. So that I think that basically until now, solvers, SMT solvers and SAT solvers have been written as if to operate in prison, right? They're not going to have any, they're not going to have multiple microprocessors, they're not going to have networking, they're not going to have persistent storage. There's just a bunch of capabilities they don't have access to. And with the distributed, suddenly you just have open space, right? So you can do whatever you want to do. And so you have more resources, more freedom, more opportunity for exploration and failure. We're especially excited about the work in just quantified, using this for quantified formula, where there's basically, if you're trying to solve quantified formula, it's there's really not, like, you have to make a bunch of really difficult choices early on, and you're probably going to make them wrong. So then you have to write the solver extremely conservatively, and thus things don't tend to work out very well. So I'd say the Achilles heel of SMT solvers are quantified formula. Okay, so that's the context. We want to revisit how we handle quantifiers in SMT while keeping the idea of cloud native solving. Imagine we're going to build a cloud native solver, not a sequential solver, and use that in place. Okay, so that's the context of this work. So let me illustrate with an example. So here's a formula that we're trying to answer: is this satisfiable or unsatisfiable? And okay, so I'm gonna do a series of steps to kind of illustrate this idea. So we're gonna translate this into an equisatisfiable form specifically for our approach. So bear with me for a second as we do a few steps. So I'm going to first use we're gonna remove the quantifier using an equivalence that holds in Hilbert's epsilon calculus. So we're basically going to replace the existential with using this. So let me just read this to you. So the existence of x such that not p of holds is the same as not p of holding on the x that we chose such that not p of holds. That's an equivalence that you can that Hilbert's epsilon calculus gives you. So we're doing that translation to get rid of the quantifier. Okay, you'll see why in a few minutes. The next thing we can do is we can translate this, and this is equisatisfiable. And so again, we're doing this for kind of a quite specific reason. So I'm introducing a new logical constant I'm calling L1, which is set. I'm mapping to the Hilbert term, and then I'm replacing the use of the choose term with L1. And I'm using conjunction to break this apart. Okay, I'm gonna basically apply the same trick again. So but now for the universal. So for all x such that q holds is the same as q on the x that's chosen such that not q holds. And so the idea with the choose is that if there is no if there is no x such that not q holds, then it chooses any value. And so if you kind of puzzle about this for a few minutes, you'll actually see that those are equivalent. So we're going to apply that same approach. The details are going to get a little tricky here. It's because Q in our case is P of X and not P of L1. I'm just deriving this from the formula. So we apply that transformation again, and then I'm going to do that same equisatisfiability trick where I introduce a new logical constant L2, and then I break things apart. Okay, so that's our formula. So why is this nice? So the thing on the left is a quantifier-free SMT abstraction, and the thing on the right is all conjunctive epsilon theory, and that's going to have some advantages. This is the sum total of, this is all of the axioms you could ever add. So it's saying Q of t, for Q of t implies Q of choose a Q such that X holds, where Q is any well-formed formula, T is any term, and X is a variable. And so so how we prove this formula unsatisfiable is we find axioms, conjoin them onto this, and then show that becomes unsatisfiable. And it turns out we're going to be able to do that without in the SMT solver such that it doesn't need to understand quantifiers. Okay, so refinement is just the search for relevant axioms which can be expressed as refinements in the quantifier-free abstraction. So here's an example. I'm going to leave T free for a moment. We'll talk about that in a moment. So I can conjoin on to this this new formula, and this is derived from the axiom schema. And well, I'll fill in the details a little bit. I haven't told you what T is, but just a little bit, bear with me for a moment. So this abstraction is free from epsilon theory, and there has no quantifiers. Okay, so I've basically now abstracted away a lot of those details that we're trying to get rid of in this, and we could actually reason about this in pure, as long as I consider L2 and L1 as essentially uninterpreted logical constants. This is now entirely SMT. Okay, now we're free to choose any T so long as it's a well-formed term. Now let me just show you how I built this. So this formula is based on this axiom schema. Let me just show you that to make sure that you agree. The Q in this instance is from before. We can choose any Q, but it turns out that there's only so many Qs that would work. And then this sort of falls out. So it turns out that, I know the details get a little hairy here, but so L2 is basically choose X such that Q of X holds. So that's why I'm able to get from here to here. Okay. Great. So now let's choose a T. And so here I'm just going to do a bit of magic. So bear with me. I'm just going to choose L1. Okay. That's the one bit of magic I have to do. Okay. So now this quantifier-free, epsilon-free abstraction is now unsatisfiable. Why is that? Well, P of L1 and not P of L1 is false. And then, of course, the negation of false is true. And then true of implies something is then just the something. And then, if you'll notice, this formula is just the negation of this formula. So now we're done. So we just proved that our original formula is unsatisfiable via an abstraction to essentially a quantifier-free and epsilon-free SMT formula, and we've used the structure of the epsilon axioms to derive the abstractions that we needed. So we basically were doing the refinement in epsilon, and then we're doing the solving without epsilon, and there's no quantifiers in there. Okay, I basically said that. Okay, so then this is something I find quite intriguing, that the syntactically from L1 and L2, this is your axiom schemas. This is the space you need to search over for that and the T, right? Because this is totally defined by what's here in our set. So the only choice we really have is T. So we basically produce axioms of this shape, which is syntactically already predefined. We have two axiom schemas. We can generate a bunch of them, and then we just need to choose the T's for each one, and that's really our only degree of freedom, which I find quite charming. So just to give you an idea, I'm not. This is motivated by the sort of move to distributed, but I'm just going to show you a sequential algorithm so you get the idea. All right, so this is limited to unsat, and we're just going to walk this formula through. So we take the formula, we abstract away, so that gives us our SMT abstraction using L1 and L2, which are uninterpreted here. This M represents the axiom schemas and the mapping from the logical constants to our interpretation over in the Hilbert's epsilon, and then we assert in the SMT solver that SMT formula, and then basically we just solve, right? And if it's satisfiable, we get a model. We can do a bit of work. I don't want to get too into the details, but it chooses the schema that's relevant to the model. And then uses the axiom schema to instantiate term and Q. We assert that. We go back and resolve, and now we're done. So basically, this is an algorithm that kind of implemented the example that I walked you through. Now, what I'm excited about is actually distributing, right? So one could imagine, and here I'm waving in my hands quite a bit, but one could imagine, having 3 or 10 or hundreds or thousands of loops all iterating on this procedure over a shared data structure of, some of these data structures would become shared. Maybe some of them are eventually consistent. Doesn't really matter. Okay, is this beautiful? I think so, because unlike other SMT methods for quantifiers, we preserve the propositional structure in the formula. So I think this is quite nice, right? Here's a quantified formula, here's the abstracted formula, we get to keep this negation here, we get to keep the and here. So we preserve the structure, and thus if we have a really large formula with quantifiers nested all over, we're not doing some sort of transformation where we're pushing the quantifiers around or so on. We're keeping things where they were, but we get to keep the propositional structure. It's a bit different. I don't know if it's going to turn out to be a massive advantage, but I think it's charming. And then, as I said, it gives a rise to an abstraction into SMT. Which I suspect will be of a benefit, but I don't know that for sure. I think it's charming that the space of possible refinements is just these T's. I basically said that. So if you compare this to previous approaches such as like E-matching or the model-based instantiation methods, I don't know how to really define this, but those methods feel much more operational, right? You look at a data structure, like with the E-matching, you look at the current data structure, you walk over it, you sort of pattern match for certain things, and then you're trying to mine that structure for refinements, and the same with the model-based instantiation method. And I think that the structure of the Hilbert epsilon defines the space of refinements in a way that I think is less operational, and I think will be more easily parallelized or distributed. And then if you sort of compare to Skolemization, what I like is that we're left with this partitioning, right? So the Skolemization tends to, I think Skolemization has a place it's doing something also quite important, and maybe some sort of make it. So one thing is you could use mixtures of these techniques. So it may be that for certain parts of the formula you can apply this technique, other parts of the formula you can apply Skolemization. But I think it's I like the fact that you've partitioned the thing into two parts where you have just conjunctions of epsilon formulae, and then the propositional piece of the structure independently. Okay, is this useful? I don't know. Okay, so now just to have one more sort of gushy slide on sentiment. So things I think are really amazing about Andreas is his relentless pursuit of developing ideas. We were talking about during lunch that the quote that sticks in my head is, "But Byron, have we got to the essence of the problem?" Or "Tell me the story again. What are we doing again?" So I remember in the Terminator days, it would just be over and over and over again with him pushing harder and trying to get to the essence and boiling away all the parts that were sort of they were there, they were in the it was sort of that's just kind of details. What's the essence of the story? And I find that really charming. I think that Andreas is extremely sharing of his resources and his time. He just met some, multiple times I've seen him be very selfless and share things, and people didn't realize he was doing that work, and it made people around him better. Incredibly insightful and creative. I think that we see that from work on SLAM and work on Terminator, that the insight and the creativity is pretty outstanding. He's also incredibly funny. If you know him, you know he's funny. In fact, I'd say 75% of the mails I read from him make me laugh. That's I considered sharing them as screenshots, but then I thought that might be inappropriate because many of the emails are ridiculously inappropriate. And so I feel very fortunate to have met Andreas when I did at the stage of my career I was, because he really taught me a lot about how to do research, how to write, how to think, and I think it's really helped me in my career along the way. So thank you very much.
Questions for Byron?
That's in my office. That's in my office in East London, in Queen Mary.
in practice, when you're doing this distributed solving,
Yeah.
what is the limiting factor? Is it the solving that you're doing in each of the compute nodes, or is it the communication between them?
I don't have, I'm not going to be able to give you an authoritative answer on that because we're trying to figure that out. Like there's cases where it's either. One thing, yeah. Yeah, I think it'll change over time. So I don't think the dust has settled enough to say that reliably.
Do you think a different computer architecture, like a GPU or a cluster of GPUs, could help?
Potentially, I am. So at Amazon, we're building our own hardware, accelerators for machine learning, and I actually we're on multiple projects actually working with that team. So proving the correctness of some of the hardware and also proving properties of the compiler. And a part of my motivation for wanting to work with that team is to sort of build up enough trust with them I can start bugging them about these questions. Yeah. So it is my belief. Let me say it more generally. I believe that sort of planning as a so lots of intriguing facts. Like James Bornhold has this paper where the fastest SMT solver is actually on an iPhone because of the memory architecture on the iPhone. So there's something around what hardware support would you need to make things fast. But our first challenge is I'd say the bigger challenge we have is the volume, the addressable market of this. Like we're getting 1 billion calls per day or whatever, 5 billion calls per day to the solvers. That's not really at the volume to justify starting to burn hardware yet. So. Okay.
Oh, I had a question whether you see this distributed solving, you could also imagine like distributed model checking or distributed verification, like push it up one more level maybe. Like, do you think that, I understand why you're doing the solving specifically, but do you think that same idea could hold?
I'm a strong believer in it, and I have no experimental evidence to justify my excitement. It makes intuitive sense to me. There's a Francesco at Facebook had essentially a distributed abstract interpretation, you will, and he swears by it, and it seems like the results are good. I don't have those results. And then, I mean, the challenge is of course, like if I remember when Tom and I were doing SLAM, I don't remember, Tom, if you remember this, that Bill Gates came to look at the SLAM, like there was a tech fest. So Bill Gates came in, there was a graph of like, here's all the driver properties and here's all the big table. And he's like, so if you had 200 machines, you could do it faster? And I'm like, yeah. And he's like, do you want 200 machines? And I just thought about keeping Windows NT up to date. And I'm like, no, absolutely, I do not. Yeah, exactly. Yeah, exactly. So that's kind of what I'm saying is that there's sort of there's embarrassing levels of parallelization available to us. But yeah, I am a strong believer that ultimately we'll find. I think there's some work here. I don't want to turn this into a talk about Dirk's work rather than my own. But you might talk to Dirk because I think Dirk has some preliminary results that might be kind of interesting there.
So I would like to know what are what is the, let's say, the power of these reduction techniques, that because you have shown on an example with the, let's say, one alternation, but how far one can apply this? Is this a general technique that you can apply it for a fragment of logic, or It's a way. I mean, it's I believe it's as expressive as first order logic. So it can handle everything. Like, it can handle everything.
That's my belief. Yeah, that's from what I'm reading and seeing. That's true. My implementation of this approach right now is me with VI substituting characters. So these characters get really hairy. Like the syntactic details of this approach get really hairy very quickly. So it breaks your brain. So what I need to do is to implement it to see it. But in terms of in theory, I believe it's. I mean, Hilbert developed this as a semantics for first order logic. Yeah.
Okay, and now in terms of practical impact. So when you distribute, how the structure of the formula, I may have equivalent, let's say, formulas having different structures, but maybe the distribution of their, satisfiability problem can be more or less easier. I don't know.
So I think, I'm not sure if I understood your question, but let me answer another question I get that's very similar to that one, and then you can come back at me if that wasn't. So there's a technique from Ryan Hula where rather than having a bunch of machines all operating on the same query and then sharing conflict clauses, what he does is it's called cube and conquer, where he looks for cuts. He looks for formulae where he can break the two things apart. And then now you've partitioned this piece of the space on this solver and this piece of the space on that solver, and then you can put the results together in a pretty natural way. And he's getting really big results there. So like he's proved the Pythagorean triples problem with that approach. And I think he has a new proof of the happy endings problem, which I think is with that approach. But it takes Marijn Hula to run it, right? So basically what he does is he runs a look ahead solver, kind of looks for the patterns, finds some cuts, and then breaks the problem apart, and does that. And so if you can kind of do that early, I think it's great. But it's hard to get a good partitioning. So this approach is nice because it kind of finds the partitioning dynamically, if you will. Yeah.
Apologies, naive questions. I'm not from an S&T background, but the CVC5 folks have recently talked about distributed and sort of centralized within the different theories. So maintaining like one kind of E-graph representation. And they've got this switch, right, that you can turn this on and off. So you've talked about distribution at a higher level.
Yes.
Is there call for distribution internally?
Yeah. So actually, this distributing SMT work is joint with them. They're Andy Reynolds and Clark are both Amazon scholars with us in the team. But yeah, it is also my belief. Yeah. So basically, if you look at the Nelson-Oppen result around, you can have multiple decision procedures and they're sharing over shared equalities that sort of streams distribution, right? Because now you have something like egg, the E-graph, maybe make that into a distributed data structure, and then you just build your thing over egg, which to me seems very appealing. So yeah, yay, distribution. Yeah.
I guess we have to move on to the next one. Thank you again, Byron.
Thanks.
Speaker is Shankar. As we heard before, Byron was the reason why we didn't see Andreas in the first half of our PhD, and Shankar was the reason why we didn't see him in the second half during the sabbatical. Shankar is a staff scientist at SRI, and you probably all took either a summer school with him, which is rather famous, or found another way to learn about PBS and the other tools being developed by him and his team. So, while we're setting up. Great.
Sure. Is there a
if you just go into the presenter mode.
Which one should I do?
The tool here. Oh no, but you're not in the.
This is what I want.
No.
Actually, let me move this around and see
if you do it in the presenter mode.
Move it around and see if that works.
Where is it?
No, I don't see it here. Yeah, I think actually I've lost control of it.
So you go to Control Center.
Let me disconnect this first, so I can find out what the thing is.
Control Center.
Which one is that?
The cockpit. And then this.
Display.
Appearance. So this is the display.
Yes, please. Yeah. And now you need to plug it again.
Just do the back and forth thing, if that works. Is that connected? Is this connected? No. Can you connect? No. You would need a new tab.
You can see that technology is. But I can do it with this, right? Yeah. No, this is fine. I can go back and forth with this. Is it? It's not okay. How do I? Oh, it'll go.
Oh, you can.
Oh yeah. Okay.
You can.
Okay.
You can.
Okay. No, it's fine. That's fine. This is fine.
Or you want the?
No, this is fine. It's fine. Yeah. Okay. So let's see the. Yeah. Great. Okay. Okay. So. I had this whole thing prepared thinking that Andreas and I were the same age. It turns out actually he's a year older than I am. And, so that whole thing didn't work out. And I'm thinking, how did you grow up so quickly? Okay, So, he's always looked so youthful that I would not have assumed he would be a year older than me. But, for someone who has worked on liveness, the kind of defining feature of Andreas is that he's never satisfied. He's never really feels like he's gotten to the goal. It's always something else. So, I assume it'll be the same way even at this stage in your life. It's always going to be something else. So that's one. The talk is really about theorem proving and living in a theorem proving universe. It kind of touches on many of the themes that people have already spoken about earlier today. It's actually a bookend to Doug Bayer's talk. I'll be saying the opposite of what he said in many ways. How many of you here have not used a theorem prover? So, okay, just one person, that's good. So you kind of know what I'm talking about. And what I'm talking about in this is really an extreme version of this. That is, if you get inside a theorem prover, stay there, never leave. Okay, do everything you can, everything that everybody talked about today, just stay within a theorem prover and do that. Now, I've given the exact opposite talk also. I've given the other version of it, which is break everything down into individual pieces and reuse them. And reconciling the two is a large part of the challenge in doing this. But in this talk, I'm advocating staying inside a theorem prover and working with it. So I got into theorem proving more or less by accident. I actually was hoping to study AI, but the only part of AI that I really understood and liked was theorem proving. And so where I was studying was actually a great place for this. And this theorem proving subject looked like it was sufficiently obscure that no one would actually trouble me, that I could literally toil in obscurity working in theorem proving. This would be a very comfortable place for me. And when I said this once, Lenore asked me immediately, so how is this obscurity thing working out for you? It's been working out great, thank you. Okay. I have no problem with it. All I need to do is really just shut up and program. And so the thing that's been happening is that in the 80s especially, there was a lot of great activity in theorem proving. And formalization really became in many ways kind of, it wasn't a solved problem, but it was clear that it was a solvable problem. And this is what the work that we did in the 80s provoked Boyer to proclaim that no one's ever going to say this can't be formalized. In contrast with what DeMilo, Lipton, and Perlis said about if mathematics were one of strict logical, if the mathematical process were one of strict logical progression, we would still be counting on our fingers. Proving things like the incompleteness theorem is way, way beyond counting on your fingers. Please. Mm-hmm. But that was long before the criticism they invented it. Well, Alan Turing probably came up with inductive. Euclid came up with inductive. Mm-hmm. Yeah. Yeah, it's all gone. Yeah, that's right. Mm-hmm. And nobody seems to, everybody remembers his critique. Mm-hmm. Yeah. Nobody remembers that he was 4 before he became again. Right. Yeah. So, so the idea then is really about doing formalization well, making sure that you can actually capture the mathematical structure, the mathematical beauty, and make it so that it's automated in a nice, facile way that brings out a certain level of understanding and insight that the human being can extract from the automation. So supporting the human being in this process is really important. Being able to converge on the mistakes in your formalization, and there are going to be hundreds of them. I make mistakes virtually every few seconds that I type. I get something wrong. It's really hard for me to get things +1 or -1, and this is something where the automation, the theorem proving really helps me a lot. So for me, logic is the study of the interplay between language, meaning, proof, and computation, and this is exactly the defining drive of Andreas's work as well. It's exactly this interplay that he's been studying with contributions to all of those topics out there. And so the question for this talk is really, should we replicate Andreas within a theorem-proving universe and make sure that all of these things can actually be done inside a theorem prover, not with a theorem prover, but operating inside a theorem prover? I'll answer the question at the end. The history of this goes back a long ways. It goes back to a guy called Ramon Llull, who talked about reducing all knowledge to first principles. This was not something new. I mean, Aristotle had talked about reducing all knowledge to first principles as well. But what Ramon was talking about was developing a symbolic notation and conceiving of a reasoning machine, some way of mechanizing it. And he was a kind of a religious scholar. So what he wanted to prove was certain religious precepts could be established by reasoning. And the Pope wisely said, if you apply rational thinking to religion, you're confusing faith with reason, and condemned his teachings. I feel like in the same situation. When I say these things, I feel like many of you will have the same reaction as the Pope, that I'm confusing theorem proving and pragmatism. And so you guys might play the same role as the Pope. Ramon Llull, by the way, is also the founder of social choice theory, it turns out. I found out from a talk that Fouquier Collatus was giving. The second big person in this was Gottfried Leibniz, who talked about having a universal language for expressing concepts and a machine that could essentially crank out the truth in this universal language. And he was quite lyrical in proclaiming what this would get you. So what must be achieved is in fact this, that every paralogism, something that is kind of like a logical error, fallacy, be recognized as an error of calculation, and every sophism, some way of actually reasoning deceptively, be expressed in this new kind of notation, appear as a solecism or a barbarism. That is, it should look like a grammar mistake. When you try to pull a fast one in terms of the reasoning, it should look like a grammar error, to be corrected easily by the laws of this philosophical grammar. Once this is done, then when a controversy arises, disputation will no more be needed between two philosophers than between two computers. Computers is, of course, people, human beings doing the computing. It will suffice that pen in hand, they sit down to their abacus and, calling in a friend if they so wish, say to each other, let us calculate. So this was kind of Leibniz's kind of glorious vision that he had all that while ago. And none of this really came to fruition until roughly the middle of the 19th century, when the age of reason really started with someone, with say George Boole. It turns out Hermann Grassmann was a big figure as well, Richard Dedekind, Giuseppe Piano, Gottlob Frege, Charles Sanders Peirce, and so on. So the 19th century was a big deal. But the mechanization of automated theorem proving really started with Martin Davis programming a Pressburger arithmetic procedure. And this was an interesting quote. Its greatest triumph was to prove that the sum of two even numbers is even. Try typing that into one of your theorem provers and see if it does it. Okay, that's that's not something to be embarrassed about. Whereas I think many modern theorem provers actually do leave a lot to be desired. So the kind of development, I'm missing out on Noel Shaw and Simon and Hao Wang and Davis Putnam and many others, but focusing more on the proof checking branch of theorem proving, which is started with John McCarthy, and later on De Bruyne picked up the mantle with Automath. Woody Bledsoe is actually a pioneer in automated proof checking. He was the person I learned theorem proving from in the first place. And when I was doing my thesis, he told me that he had actually done a major proof checking project. And he checked Morse's set theory book. But it only came to light recently that there is actually a record of this. There is a Sandia report on the project that Woody Bledsoe did. And it's a reasonably impressive piece of proof checking. The big kind of revolution in theorem proving was really Bob Boyer and Jay Moore's theorem prover for pure Lisp. This is what actually made a lot of what we can dream about now possible the kind of 40, 50 years ago. So this was a theorem prover they developed initially at Edinburgh, then mostly at SRI, and that's what I did my thesis on. The LCF approach, due to Robin Milner, is also a kind of dominant strain of proof checking. So going back to this Boyer-Moore theorem prover, the current version is called ACL2, and the logic that it supports is pure Lisp. It's essentially applicative common Lisp, and you can write, for example, a function like reverse of x, and this kind of thing. You can append the reverse of Cutter of x with the singleton of the car of x, and the theorem prover automatically proves termination, that it shows that this terminates. And then you can give it a theorem like this, that the reverse of x is equal to x, and it proves it automatically. This is the only formula I really have, I think. I don't think I may have a few others, but the theorem prover is magnificent. I mean, it proves, it picks the right induction, brings in the right lemmas, the rewrite rules, and in the proofs I was doing, these were enormous. I mean, the chain of rewriting that was needed, because there were layers and layers of formalization going on. The theorem prover was truly magnificent in doing this. Just to give you an example, one of the proofs I did was the Church-Rosser theorem. And initially I had a lot of difficulty with it, but then Boyer suggested that I use the De Bruyne representation, which I didn't know what it was. When he finally told me about it, that was exactly what I needed. And in a single night, I was able to actually do the main part of that theorem. That is, once that's done, you know it's there. And this is a proof that people have struggled over for decades. So this was quite a big deal to be able to do a proof like that in a single night. And today you can take PVS and you can actually, in a sitting that is in 30 minutes to 1.5 hours, you can prove a major theorem. That's not unreasonable. You should expect to be able to do that. The NASA lib has a bunch of major theorems, and when you ask the people how long it took them, they said lunch. Okay, that's how long it took. So this is something that you should be able to do. The Jens's 16,000 line proof was monumental. I think that's really something where it takes tremendous concentration to pull off something like that. So the thing that this led to is this notion of what I call the computational Sapir-Whorf hypothesis. That is, language impacts, formal language impacts the way that you can formalize and automate reasoning. This is not widely appreciated. It's not the case that you can just take any language and layer automation on top of it. It really, good automation comes from the features of the language kind of exposing certain reasoning possibilities. And so Church's higher order logic is a good example of this. It's adequate for doing virtually all of math, and it's almost entirely executable. So this is something that you can capture, and many systems are actually based on higher order logic. And PVS is an instance of this. Whoops, the thing is cut off here. I compressed the wrong thing. But the main thing I want to show here is that the kind of interplay between language and automation that I'm talking about really comes to the fore in the way the type system works. So here you can have, for example, types like the factorial returns posint. And that's something that if you didn't have that cached as the type of factorial, it would be a pain, because the n choose k, you're going to use factorial as the denominator. You're going to use the product of factorials as the denominator. So that little bit of type information, knowing that it's positive, that the product of positives is positive, helps you say that the denominator is not going to be 0. And it cleans up math. It actually adds a lot of clarity to computation as well, because a well-typed program now, unlike Milner's claim that was false for ML, a well-typed program can never go wrong. Okay, it can only run out of stack, or it can run out of heap. Okay, that's a significant win in terms of a clean property that you get. This example of n choose k that's hidden there was interesting, because I claimed that it was an integer, that it was actually when you take n choose k, that you get a positive integer out of it. Unfortunately, the definition on the right-hand side is obviously a rational number. Okay, and so the theorem prover says it's a rational number, but show me that it's an integer. And you can go back and look in math book after math book after math book. This basic fact is missing. And it's no less trivial, it's no more trivial than the facts that they do establish. And this is something that's missing, and math expositions are filled with these kinds of errors. So you'll find at least one in every facing page. The other thing that's kind of been important is having large libraries. And this is something where I think Lean is doing a really remarkable job in getting mathematicians to fill out this thing called MATLib. So that's growing pretty rapidly. So the other systems also have large and growing libraries. So this is, again, something that would be a burden for you if you were building a bespoke tool for your particular task. So having these libraries is actually a big win. And having these libraries centralized around a single theorem prover is a useful thing to have. So this, to build some new inference system and try to bring in these libraries would be a huge amount of work. There are just like hundreds of man-years going into the development of these libraries. Okay, so what can you do inside a theorem prover? The first thing is obviously you can formalize, and I assume many of you had the experience that just the mere act of formalization reveals a bunch of errors. Just writing the definition of n choose k forces you to think, why is the right-hand side a positive integer? So it forces you to think about that. So that's one kind of thing. The other is kind of modeling. So unlike a programming language, formulas don't need to be executable. So you can write models that are not non-executable. You can also write models that are executable. And you can write them at varying degrees of efficiency. You can write models of the physical world. You can write models of human beings. So these kinds of things are really helpful in developing software, because software does not operate in a vacuum. You do need to know the models under which you're operating. You may have, for example, models of computation, models of communication. You may have physical plant models, fault models. So there's a whole bunch of these that you can capture of these. And this is something, again, that has been a popular activity in theorem proving, which is that you don't just model the program under analysis. You model the full environment and you prove properties under that environment. Then you can go further and do proof. And proof is a very, very efficient way of finding mistakes, both in your formalization and in the proof itself. So you can correct your reasoning. And you can use theorem prover in many, many, many creative ways that these bespoke tools do not support. So you can use theorem provers for exploration. You can use them to kind of just do symbolic execution, for instance. You can use them to find abstractions. So there's a whole bunch of things you can actually do creatively with a theorem prover. Now, many of you claim to have used theorem provers, but I don't know whether you really truly exercise your imagination in using it. But if you do see the possibility of using the theorem prover in imaginative ways, you'll find that it's really mind-blowing what you can do with it. So you can use it for simplification. You can use it to do rewriting and symbolic execution and so on. This is, again, something where you can, if you wanted to use a theorem prover as a backend, but you can actually use it as kind of like a kind of computer algebra system. You can use it for constraint solving. Byron's talk was about this, about SAT and SMT solving. So you can generate both counterexamples, test cases. You can check for validity of formulas. So this is, having this kind of automation is really helpful for a number of applications. In fact, it would be quite difficult to do this without this kind of automation support. And this is what PVS actually, we intended it as a theorem prover that you lived within, but a lot of people are using it as an SMT solver because that's all that existed at that point. And then, we slowly started kind of pitching out the SMT solver part of it in the 90s. So we started providing standalone SMT solvers. But if you look at the work on predicate abstraction, for instance, it was done directly using PVS as a SMT solver by Suzanne Graf and Hassan Saidi. So you can embed other logics. Again, we did a bunch of these in the 90s, and we're still doing work like this. You can embed other calculi. You can embed programming languages. You can embed programming language semantics. You can embed modal logics, deontic logics, cryptographic protocols. So a lot of these things you can do with different degrees of shallowness. So that by shallowness, it means really how much of the syntax of the target logic are you capturing in the host logic. Okay, so in the host logic, that's the degree of shallowness. And the more you capture, the more meta theorems you can prove. That's the idea. So the more ability you get to prove meta theorems about it, but you may not want that. So you can construct abstractions. You can do this automatically. I mentioned the work on predicate abstraction already. You can formalize static analysis as a lightweight theorem proving exercise. And finally, you can program, and you can program with efficiency, with correctness, and you can get both low-level and high-level code out of it if you wanted. You can program down to the machine code level if you wanted, or you can program in a very, very high level if you wanted. And so you can you get this full spectrum of abstraction. So in the end, what we are engaged in, the activity that we're engaged in, is something I call abstraction engineering. And in abstraction engineering, you're looking for certain sweet spots where the abstraction actually buys you a lot in terms of the properties you want and the facility with which you can derive those properties at this abstraction sweet spot. So it's not about more or less, it's about a sweet spot in the abstraction. And that's what you can get with these theorem provers. So how much time do I have left? I need to maybe hurry up. Okay, that's not bad. I can do that. Okay, so why would you do this and not the other thing, which is just use a theorem prover as a backend tool, and that way you can call perhaps a model checker, an SMT solver, abstract interpreter, type checker, all of these things as backend inference tools. Why would you not? Why would you do the idea of living inside a theorem proving universe instead? And the kind of thing that you get is that the outside world does not make sense. Okay. It doesn't even try to make sense. Okay. In a theorem prover, if it doesn't make sense, you're not going to be able to prove theorems, because that's part of what you get out of it. And doing a proof, you understand. Okay. So that's a kind of important point about the use of staying within a logic and embedding all your needs within that logic. So logic is also a good way to communicate. It's really hard for people to read code, for instance. It's who knows how people interpret it. Whereas logic is actually something that's both machine-friendly and human-friendly. It forces you to think in a way that just writing and running code does not. Although you can write and run logic as well. So the theorem provers catch lots and lots of errors. They allow you to shift abstraction layers in a way that sometimes your bespoke systems don't. They don't support this. You can deal with both computable and non-computable models. You can model the physical universe as well as the virtual universe in proving properties that are of interest. And you can actually use logic as your lingua franca for what all your tools actually speak. They communicate in terms of the core logic. So that's something that is really an advantage, because often there are semantic impedance matches when tools actually communicate different things. So by integrating these tools within a single coherent logic, you make things a lot more unified and seamless. So the limitations, though, and these are serious limitations. There are good reasons why I can speak through the other side of my mouth as well. Okay, which is that proof is not for the faint-hearted, and this is not. It's not as insurmountable a barrier as you might think, but it does take, I don't know, a few hours to a few days worth of training to get to this point. So I have lots of undergrads doing this stuff, and they are actually much better at doing proof than I am, and they get there very quickly. So it's not insurmountable. It's just that we've not done a great job of teaching people that this is a worthwhile activity and they should get good at it. State and interaction are not easily modeled. So when you generate code from PVS, for instance, you can generate C code, and it is stateful C code. It is going to work just the way your handwritten code would work. Okay. But you can do much more expressive things in PVS that if you were to handwrite in C, you would spend a long time trying to get it right. In fact, you would probably never get it right. But in PVS, it would be no problem to write it and generate the C code for it. So there's certain things where programming language or a bespoke system gives you kind of more freedom than you would get. There are certain kinds of data types that are hard to capture in a logic, but that you can get away with in a programming language. Because a programming language does not have to make sense. A logic does. In applications such as optimization, you sacrifice soundness. And so this is kind of something that's hard to do in theorem provers, although as Byron said, you can have a switch that gives you, a little bit of unsoundness. Sometimes that's useful. It's not a bad thing to get to some results quickly. But in general, you would have a soundness problem. The other challenge here is that proofs are another artifact to maintain. That is, in addition to the code, you're maintaining the proofs as well, and that's usually been a challenge. And so it's really hard to replicate the ecosystems that programming languages like Python and Java and C include. So they come with everything. So this would be a huge amount of work for anyone working with theorem provers. And the reason we build bespoke tools is that we can actually take advantage of some of the optimizations afforded by the narrowness of the domain. So that is something that we can take advantage of that sometimes it's hard to do in a system as general as a theorem prover. So these are serious challenges. So yesterday it occurred to me that I had actually made this case a long time ago. Sometimes you forget that you've actually said something before and you could go back to it. So in 1995, I gave an invited talk at the Mathematics of Program Construction, and I wrote a paper called Computer-Aided Computing, and I made pretty much the same points then. But on the other hand, we've actually spun out the SMT solving. We've developed a whole series of solvers leading to Yikes. We've spun out the model checking. We used to do that inside PVS first. And so the kind of lots of reasons for doing this, and in particular, this is what people asked us to do. So we ended up doing some of that. On the other hand, now I believe that we should not have done that. We should have gone for the long view. We should have stayed inside the theorem prover. We should have developed much of this inside the theorem prover. And one of the cases for this is made very beautifully by Cesar Munoz and John Rushby, in which they showed how they built a system called PBS, where they embedded the B method in PVS. And it's only like about 25, 30 lines of PVS. You get something that's actually better than the B tools. Okay, so you can leverage PVS as a kind of universal proof obligation generator. So it generates the refinement proof obligations just by writing the right formulas. In the Festschrift, I show this for Floyd's method. You can adapt it in many other ways. So that way you get all of this automation and theorem proving that you have. At the same time, you're operating as if you built a bespoke tool, because it's generating the same proof obligations that a system like Daphne or Boogie might generate. In fact, one of the things I have done is captured the Boogie memory model in PVS. And again, it's like 20, 25 lines of code. It's literally minutes worth of work to do this. I did it while Peter Muller was actually talking. So it's a very simple thing to do. And the amount of stuff that the theorem prover gives you to do this is hard to replicate. So the nice thing about this kind of integration is now anything that you bring in is automatically usable within this framework. It's kind of semantically seamless. So that's the important advantage that you get by staying inside the theorem proving universe. So this is achievable. The systems that we have are entirely capable of doing this. And if 30 years from now, just like engineers stay within MATLAB, I wouldn't even say 30 years, I would say less. I'm being very conservative in my predictions. But if you're staying within a theorem proving framework, you shouldn't be surprised, because just like MATLAB gives you these advantages of staying within one framework and doing all your modeling, we can get theorem provers to a point where they give you the same advantages. And so there's quite a lot of work to build on. And in particular, you can reason about theorem proving itself in a theorem prover. So that's something that started with Boyer and Moore's meta functions, and there's kind of a nice tradition of work doing that. And we kind of can already generate efficient code. There's really no reason to write code directly. If you write it in a theorem prover, you can get good code out of it. You can get code that's memory and type safe, as I mentioned. And the other thing is that we are beginning to model a lot of things. So you're getting these models of a lot of the artifacts that you might need to work in this world just like you would with MATLAB. So that's something that I think is happening. And we're figuring out how to extract logic from natural language as well. So this actually was another prediction that Vannevar Bush made in his monumental article, As We May Think, which heralded the modern world. And in that, he actually has two riffs on theorem proving. And in one, he says logic can become enormously difficult and would undoubtedly be well to produce more assurance in its use. We may someday click off arguments on a machine with the same assurance that we now enter sales on a cash register. So that's, he expected that theorem proving tools would be just a part of a scientist's workbench. So conclusions, the main message that I've repeated over and over is that we can go back to this Leibniz dream and think of logic as a universal formal language in which we can integrate a bunch of inference tools, embed a number of programming languages and calculi in a semantic form, and carry out proofs at scale. Not just proofs, but a lot of other simplification, abstraction. A lot of these operations can be done. And the last 40 years have actually yielded a number of impressive advances in automation. We heard a lot today about Andreas's work with his colleagues, and that's I think something that we can build on. And it's a kind of you can create an ecosystem where you have it vertically integrated. You can reason about everything from hardware all the way to the distributed systems and perhaps even user interfaces and so on. So this opens the door to sitting inside a theorem prover and operating with all of these models available to you. So you can imagine that you can reason about human cognitive models, you can reason about cyber-physical systems, you can reason about the combination of these things, and essentially make the world safe in a way that would be hard to do if everything were fragmented. So, to answer the question at the beginning, since Andreas has cracked the meaning of life and slayed the halting problem, he shouldn't live inside this universe. He should, I think, be in charge of watching over it. So that's the position I think I would reserve for Andreas. But the takeaway is never leave the comfort and clarity of a theorem prover. Thank you.
Any questions for Shankar?
Well, suppose somebody wants to start now using theorem prover. There are several alternatives. What would you advise him? I mean, Koch or yours or Isabel Hall or I don't know. And
so
each comes with.
Mine who passed away, Drew Dean.
Huh?
So he said use the one that the person in the neighboring office is familiar with.
Yeah, that is so good. No?
So it's really important to have access to experts. I recently ran a boot camp, and it's really sobering to see what the students struggle with all of these systems, by the way. I find many of them actively dangerous. If you get people into these things too early, their mind gets frozen into this pattern of thinking, and then it's no longer math to them. It's whatever that system is. So the key thing here is that you really have to have a certain level of mathematics
Shaka, can you use the mic? Otherwise, everyone here.
I think I'm next, right? So, well, first of all, a correction. I didn't say we should have an off switch for soundness. That was Rupak's idea. I actually am quite like religiously opposed. Like soundness is something I've actually had to push on very, very hard. So I think I'm adding.
I didn't say you advocated it.
Okay,
You mentioned it.
Yeah. Tell me your thoughts on this sort of trend where people are training large language models over proofs, potentially to make an assistant to help you use these provers. And does that because now this gap around you need to sit. Basically, your answer to the last question is you need to sit at SRI next to people and know how to use the tools, right? But maybe now with the large language models, this world is actually not far away from us. What's your opinion there?
No, it's still quite a distance. So the people for whom this actually helps a lot are those with considerable mathematical maturity already, and it really is not something where the kinds of problems novices run into. The large language models don't address, because that's such a wide space. They address things where people have gone deep, and that's why you have more data. And so the experts somehow find value in this because they are operating in the same space as the training data, but novices really just hit a roadblock and they're not able to make progress. The other thing here is that I'm not so confident that the results people are claiming are actually things you would see in the wild. In fact, you don't right now. And I suspect it's in a large part because they're not able to separate out the training and test data. So you're seeing there are lots of similar proofs, there are lots of cut and paste things, so you end up duplicating a lot of the training data and the test data, and that's why I think you're seeing numbers that don't get borne out by things in the wild. Having said that, I think that a lot of the activity in doing proofs is, some of it is high entropy, a lot of it is low entropy, and if these language models can capture the low entropy stuff, they really do relieve considerable burden.
Do we have any last question for Shankar? Andreas?
So it's somewhat related. You mentioned the inference of logic from natural language.
Yeah.
There is this gap, right, between the
informal formal gap. Yeah.
What do you do about it?
Yeah, so this is, I think, a serious burden for all of us who work on formal methods, that the number of papers written on how you ask even experts to interpret temporal formulas, they can't tell you what these temporal formulas mean. And quite often I find myself proving something that isn't what I intended to say. And so the kind of approach to this is, you can think of it as a multimodal approach. So on the one hand, there are stakeholders for whom natural language makes plenty of sense. There's a certain interpretation they have of it. There are people who can read the formulas. There are people who can read the examples, scenarios, turning the formulas back into natural language, generating models so that people can look at the models and see if this is what, or visualizations. So all of these are helpful devices for bridging this formal and informal gap. But we need to go both directions in order to do this well. So we need to be able to take formulas and render them in natural language, and take natural language and render them into formulas. So there is a system we built called Arsenal. We built 2 versions of this, and you can go to GitHub and try it out. It's kind of, it's a pre-LLM model. It's only now that we're actually doing it with more with LLMs. But
so to extract logic from natural language.
Yeah, but you can go the other direction also. So what it does is it reformulates it so that you can check, a human can check that the, even someone who can't read the formula can check that the interpretation is right.
Thank you again, Shankar.
Yep.
So before I hand to Andreas for the closing remarks, I would like to ask the speakers, colleagues, and PhD students to stick around for a group picture afterwards.
Otherwise, there's no dinner. Dinner.
Okay.
That's the precondition.
Change the battery and then.
Just a quick announcement. So for those of you who are registered for the workshop dinner, so we are meeting at a restaurant called
It's working. So now, right. Okay. So it's very strange to give a talk where the first slide says concluding remarks, right? So I was expecting that I will be terribly moved in the moment where I give these concluding remarks. And Lenore, in her infinite wisdom, advised me to write presenter notes. So this is the first time I have really spelled out my whole speech in the presenter's comments. And I was thinking that in the worst case, somebody else can read them. But for now, I'm fine. Okay. So first of all, let me thank you. So the 4 organizers, where are they? Well, actually, Andre could not come. So I want to thank Daniel, Andre, Martin, and Thomas for organizing this event. It came really as a big surprise. At first I hated the idea, but then I realized that I really appreciate the effort. And I also thank the speakers of today. It was a wonderful session, and I thank all the people who came to this workshop, some from far away, and so thank you, and and I hate you all for doing this to me. So. So we talked a lot about the past. And so I will retire as a teacher in 2.5 years, but I will not retire as a researcher. And so I want to expose to you the plan of what I will do in the next 65 years. And actually, I don't know what I will do in the next, I even don't know what I will do in 1 year from now. So I can talk to you about my obsessions of the moment, right? And I will talk only about 2 of those. So software model checking for concurrent programs. So we started with software model checking for sequential programs, first for safety. And since we couldn't do safety, we made it more difficult. We went to termination, right? And since we can't do sequential programs, let's go to concurrent programs. Always, if you can't solve a problem, try the next harder problem. And So actually, it may be that some things may be easier for concurrent programs. Perhaps it may be easier to find the right assertions. And then what we have to deal with is, well, the problem of state explosion, right? So now by state I mean simply the nodes in the control flow graph of the concurrent program, sometimes called the product graph. And the number of nodes grows exponentially in the number of heads, in the number of threads. And so then there is the next thing that you need to go through the paths of this product graph, and that is worse. So what really kills us, and this is what we noticed in the experiments when Rupak and Jochen, we started to work on ticket algorithm, it's the non-determinism. And it's unbelievable. So you can do tickets for, you can prove the algorithm for 2, 3, 4, and then suddenly for 5 it stops, right? You cannot. And it was really this non-determinism that comes through the scheduler of for the threads, right? So what are the two attacks? And I haven't worked on either for a long time, and then suddenly I'm into it. So the one is partial order reduction. So the idea is we reduce the program to a deterministic subprogram, and this subprogram contains a small selection of program traces and a selection of those that are sufficient to cover all the other ones. So we mentioned before the traces, the equivalence classes, and so you just pick one representative of each equivalence class, prove the correctness for all the representatives, and then you are done, right? So this is one, and the other one is parameterized verification, right? So just give a proof for every number of threads, and this obviously gets rid of the state explosion, right? If you go to the infinite, you cannot go any further, and this is one bold way to address it. And so what I'm obsessed with right now is to combine the two. And so when I say combine the two, then I mean, well, we deal with parameterized programs by applying a certain kind of abstraction that Parash Abdullah calls view abstraction. In our paper we called it Cartesian abstraction. And it accounts for the fact that when you look only at a limited number of threads, but then with this abstraction you account for the fact that there may be always some other thread who is still in one of the states that a thread has encountered before. And so now the question is, how do you proceed? Do you first apply the Cartesian abstraction and then you reduce, right? So if you first go to a larger subset and then you go to a smaller subset, or do you go first to the smallest subset and then you abstract and you go to the larger subtract, to the larger set? And this, I find this intriguing, right? If you go first to a subset and then to a superset, where are you? But the hope is that you do it in a systematic way and that you get something out of it. Okay, so this is one of the two obsessions I wanted to talk about, the combination of partial order reduction and parameterized verification. And then the next one is requirements. So I always thought requirements is so boring, right? I mean, are there any interesting questions? And I thought this is only for people who want to stop thinking. And this is referring to something that, can I tell the story? Yeah, so Rupa got this as feedback when he told Martin Reinhardt that he wants to work on testing. And Martin Reinhardt said, maybe you just want to stop thinking. And I feel a little bit like this. And obviously requirements are important, but this is not enough as a motivation, right? I mean, yes, we have these two inputs, the system and the correctness criteria, and we have to get the correctness criteria from somewhere, and from where do we get them? And yeah, so people spend a lot of time writing requirements, and they spend a lot of effort, but these requirements are in natural language. And so it feels like you write them, but you never use them, right? Because it's not a beautiful natural language, and it's very hard to read them. So what can you do with them? So one thing you can do is to transform them into formal requirements. And this is why I asked the question to Shankar, right? Extract logic from natural language. And the engineers at Bosch and Mercedes, they do not write formal requirements. I mean, they don't have the mindset for that, they don't have the patience. You need to be kind of autistic to write formal requirements. And this is how computer scientists come in, right? And so what we look at now is what if we, without the domain knowledge of Bosch and Mercedes, we take the requirements in natural language from Bosch and Mercedes and we write formal requirements. And they, I mean, since we don't have the domain knowledge, the formal requirements, they reflect only part of the meaning. But still, the question is, what can you do with these formal requirements? So can you use them for monitors? Can you use them for test generation? And can you use them to detect errors in the requirements? So can you check certain properties? And then there is a certain question. So these properties of the requirements, they are correctness requirements for correctness requirements, right? Because requirements are correctness properties. Sorry, this is what I wanted to say. So I kind of like this, who is the guardian of the guardian, right? And this you can go on forever. Okay, and so I want to finish by something more serious. So an homage to three persons who are no longer with us and who played a big role for me as a mentor and a role model. So Maurice Nivard was my PhD advisor, and for the better or for the worse, I adopted his style of advising PhD students. And that's essentially trust them and leave them alone, don't disturb them in their creativity. And I heard the complaint that, well, not all of my PhD students appreciated this kind of supervision. Then Harald Ganzinger, he was my group leader at the Max Planck Institute. And he was, his principle for guiding the member of the group was similar, right? So he told them, this is your chance, take it or leave it, right? So trust, no control, and no breathing into the neck. And then Amir Pnoeli, I mean, excuse me? Okay. So Amir Pnoeli, he was a great scientist and a great sense of humor. I remember so many jokes he made. And I'm extremely grateful because he was one of the first people who understood the interest of transition invariance. And he encouraged Andre and me and then Byron to really go on this. So I started by thanking you, and let me just repeat you. Thank you very much.
I guess we can also make room for questions to you if somebody has a question for you.
You sounded like termination for software is a solved problem. But this is... Okay, I see. So I just wanted to mention that for termination we have not even witnesses, right? So in a couple of years ago we were saying that, okay, verifiers that spit out yes or no have no value, they are useless. unless they tell us justification why the answer is yes or no. And for termination, we are still having the situation from 10 years ago or even more, where we have an answer yes or no, but we need witnesses. Let's work on this.
So we heard several talks about reducing termination or liveness to safety, and the approaches were very different, right? So transition invariance, what Lenore did, what Jochen presented. So it will be an interesting problems, yeah, to come up with witnesses that are produced by one tool and that then are validated by another one. Yeah.
We also generated ranking.
Yeah, yeah. So so Rupak's suggestion is run the program and see where it terminates.
Do we have one more question for Andreas? If not, then like.
Can you remind us what the meaning of life paper was about? Because I never actually went and read it. I just saw the title.
So the title of the paper, so there is one version which is the meaning of life, but then we realized that we were a little bit presumptuous, and it was then called Thoughts, the Meaning of Life. And life was a programming language, and life stands for logic, inheritance, functions, and equations. So just put everything into it, right? And yeah, that was in a former life when I was at DEC PRL. So most people even don't know what DEC is, right?
Did you have a follow-up with the Holy Grail?
No, not really. Yeah.
Thanks. If there's nothing else, then thank you again, Andreas. Now I need someone who knows something about photography. Where do we place people to get good light?
Not there. Probably here. With a nice background on the slides or something.
A green screen?
Then can we have